Good morning. So this is a session on probabilistic programming. My name is Jeremy Seek. I'll be your session chair this morning. And we've got 5 talks this morning, each 20 minutes. So if you're doing 15, 16, 17 minutes talk and then a few minutes of questions, we're getting just a tiny bit of a late start here, but not too bad. And so without further ado, let's hear about bit blasting from Porvogard. Thank you.
Thanks for the introduction. Hi, everybody. I'm Purva, and today I'm going to talk about a new way to reason about probabilistic programs. And this is the work done in collaboration with Stephen, Guy, and Todd. So let's get into it. So probabilistic modeling is a very widely used tool in a lot of scientific communities. Scientists use probabilistic models to account for uncertainties all the time. And to make this probabilistic modeling fast and accessible, they use probabilistic programming languages. So what are these? These are languages that support easy creation of probability distributions and allow you to compute over them. So I have an example here of a probabilistic program. I'm defining A to be a Bernoulli random variable. And then, depending on the value of A, I'm defining B, which can be either of these normal distributions. And now you want to know what's the resulting distribution of B. And finding that out might involve some calculation that looks like this. Now, this is a simple program, and that's why this calculation doesn't look as complicated. But for more complicated programs, this might not even be possible in closed form. So we want to automate this part, and that's the primary analysis task that you want to do on a probabilistic program, and it is known as probabilistic inference. Cool. Now, if people must have noticed, this program has both discrete and continuous distributions. For the rest of this talk, I'm going to refer to these programs as hybrid probabilistic programs. And such programs occur very naturally in numerous real-life applications. In computational biology, in modeling clicks on a web page, in modeling supply chains, all the time. And now you want to do inference on these hybrid programs. But unfortunately, the inference for such programs is not well supported. To give evidence for it, I'm going to talk about different approaches of inference that we have today. I'm going to talk about 2 broad classes, the first one being approximate sampling-based algorithms. And within that, we have Hamiltonian Monte Carlo, which is a very popular algorithm for doing inference, but it has limited support for discreteness. It doesn't support discrete random variables. Then we have other algorithms like Markov chain Monte Carlo and sequential Monte Carlo, and they are universal algorithms. They can support any kind of programs with discreteness, continuity, no issues. But it has well-known scalability and accuracy issues, because of which HMC came into existence in the first place. Moving on to the second class of exact symbolic algorithms. The first one we have here is based on algebraic evaluation. It's called psi. They take a probabilistic program and convert it into an algebraic expression that they try to solve. And as I said earlier, the closed form of programs do not always exist. And then we have knowledge compilation-based PPLs, such as DICE and PROBLOG, but they do not support continuous distributions. So to overcome the limitations by these tools, we propose a new PPL. It's called hybrid, and it's based on a new symbolic approximate inference algorithm. And it's based on a new form of discretization. What it does is, actually what using hybrid API user can do is they have a hybrid program, and they can obtain a discrete abstraction of it. And once they have the discrete abstraction, which is actually a discrete probabilistic program, hybrid performs exact discrete probabilistic inference on it. And as I showed earlier, there are tools out there for discrete programs. We can directly use those tools. An important thing to note here is that the only loss of fidelity in this process is coming from discretization at this step. So, okay, discretization seems like a cool idea, but it comes with a trade-off. So let me explain this with an example. We have a uniform distribution here. And here I have discretized it into 8 points. Okay. Now I want that discrete distribution to be faithful to the original continuous one. So for that, you need a very large number of points. 8 won't do it. So if I'm going for a 32-bit discretization, 2 raised to the power 32 points, then I have to represent 4 billion points. And that's what existing approaches are doing and failing to scale. So to overcome this trade-off, we introduce bit blasting, which is a binarized view on distributions. What we are proposing is take a continuous random variable and approximate it using a distribution on its binary representation. Okay, so how does this help us? You have just changed the representation. You still have exponential number of points to represent. What it does is it exposes useful structure that was opaque before. And that leads us to our first contribution. We have found a class of very common distributions, uniform, gamma, Laplace, that for these distributions, when you represent them in binary, you get a representation that's linear in the number of bits. And that's also without any loss of accuracy. You exactly get a representation of those 4 billion points. To be more precise, if you start with a mixed, I didn't define mixed gamma. So we are characterizing all these distributions as mixed gamma distributions. So to be more precise, when we start with a mixed gamma distribution, let's take uniform for an instance, and you naively discretize it, you have to represent 4 billion points. What I'm saying is, if you bit blast it, you would get a representation which only uses 32 coin flips for 4 billion points. Isn't that exciting? Okay, so now moving on, this succinct representation does not automatically imply efficient inference. Inference, in fact, is sharply hard for these programs. But we also found that when you take our representation and try to do inference on it, you get polytime inference. It's like dream of discretization come true, where we have reduced these distributions from like sharply hard to polytime class. And then we took these theoretical contributions and built a PPL around it. It's called Hybrid. It's available on GitHub on this link. It's open source. So what Hybrid API does is it allows users to write their programs as bit-blasted abstractions. You can, if you have a mixed gamma distribution, you can bit-blast it exactly. If you have some other distribution, you can bit-blast using piecewise approximations. Here I have a 5-bit approximation of normal distribution. Okay. So now I'm going to go into more detail of each of the contributions that I just enumerated. Okay, so recall contribution 1. I showed you distributions that have succinct representation. So to give you intuition about that, let's start with the most simple distribution out there, which is a uniform distribution on unit interval. Okay, and what we are doing is we are discretizing it using 3 bits, which means discretizing it into 8 intervals, and it looks like this. Okay. Now, if you were to do naive discretization, what would you do? You would flip a coin with 1/8 probability, output the first point. If it's false, you move on to the next coin, flip it, and you go on like this. So you have 1 coin flip for each interval, and that would need 7 coin flips for 8 intervals. What we are proposing is exploit the binary representation. If you exploit that representation, you can represent this distribution only using 3 coin flips. What you can do, you can flip 3 coins, each with bias half, And each of those coin flips would correspond to each bit. And if you are trying to calculate probability of one of these points, you can just multiply them and get the desired answer. And now, once you have this representation, you can just discretize x using 32 bits in 32 coin flips. OK, so uniform was a simple one. Can we go beyond this? And actually, this person from 1970 showed that you can do this for exponential distributions as well. You can have independent bits and discretize exponential distributions. So here I have the program corresponding to this discretization. It looks very similar to what a uniform would be, except the parameters of the coin flips are different now. And these are closed form. You can calculate them, and you can extend this to 32 bits very easily. OK. So these programs were trivial. They were just independent bits. And we don't need to restrict ourselves to only independent bits. We can do, as long as we can have probabilistic programs over the small number of coin flips, it would be fine. So if I start with another example, I have this gamma distribution here on these parameters. And this is what it looks like. Fairly complicated. How will you get the smoothness? And we found that it can be represented using this continuous program that uses uniform and exponential. And we know we can do uniform and exponential. So in the end, when you discretize it, you get a program that looks like this. And this would give you this discretized representation of a gamma distribution. So if we look at this program is using 3k plus 1 coin flips, 3k in the first 3 lines, and then 1 here. And now, as you increase the number of bits, you can just increase that representation to more number of bits, and you would get the corresponding program. So again, if you were to discretize to 32 bits, you just need 97 coins. We were very surprised when we found this. OK, so I just showed you guys how these mixed gamma distributions can be represented succinctly. But how does that help us in inference? It helps us in inference, specifically knowledge compilation-based inference. So let me give you a bit of a background there. So what knowledge compilation-based inference does is, it takes a probabilistic program and compiles it to a data structure. What's the data structure? It's a binary decision diagram with the weight function. And the problem of probabilistic inference is cast as a problem of weighted model counting. And it turns out weighted model counting runs in time linear in the size of the BDD. So if I can get a small BDD for a probabilistic program, I can do efficient inference. So that's what we have shown. We have shown that for mixed gamma distributions, when you compile them to BDDs, you get a representation that's you get a BDD that's polynomial in the number of bits. So take the example, the simple one that I showed for uniform distribution. And when you compile it to a BDD, it looks something like this. For each coin flip, we have one node in the BDD. And each of the B1, B2, and B3 are representing bits. So B1 would be 1, depending on whether F1 is 1 or not. And these are the weights. So as you increase the number of bits, the number of nodes would increase linearly, and you would get a poly-size BDD. Yes. OK. So great. What did we further do with these theoretical contributions? We built a PPL. And as I said earlier, it has an API that allows users to write bit-blasted programs. We provide them with a function called bitblast, which takes the bit width, any continuous distribution, the number of pieces, and the range as input. And then we have specific API for bit-blasting mixed gamma distributions. And what this returns is a fixed point number, which is a discrete structure. And Hybrid also supports fixed point arithmetic. And then we evaluated it on a comprehensive suite of benchmarks. We reported absolute error achieved within a timeout of 20 minutes. We compared with 4 different classes of PPS, which I described earlier. And Hybrid supports all the benchmarks, and it gets the best accuracy on 11 out of 19 of them. So with this, I conclude. What I have talked about today is that how the dream of discretization is coming true, how we have these class of distributions for which we have succinct, exact up to bit width, and exact up to bit width representation, and that also exhibits polytime inference. And then we have built a system around it. So yeah, please feel free to check out the paper and the implementation. Thank you.
Translated probabilistic program that you had, basically you had also that one.
Yeah.
So you have basically a comparison operator, which seems to be on the integer distribution, all right?
Yes, so once you have discretized them, you have fixed point numbers.
Yeah.
And then you can do this comparison operation on fixed point numbers.
Okay, so is this the only operator that you use on fixed point numbers, or there could be through the translation usage of some other operator?
So for mixed gamma distributions, we only need comparison. But if you have more general programs, we also support addition, subtraction, all the arithmetic operations out there. So you can write any arbitrary hybrid programs in the general language. But for the mixed gamma distributions, this is the only operator we use.
Okay, thank you.
Yeah.
Did you experiment with bases besides 2 for the discretization, like using like base 3, so instead of a coin flip, it would be like a 3-sided dice?
We did not. We only compared with binary representation, though it would be an interesting experiment to see how the representation extends when you have a 3-sided dice. My conjecture would be that it would only be a polynomial decrease in the representation.
Thank you for the great talk. So what are your sources of inaccuracy currently?
So for the mixed gamma distributions, it's only when you are discretizing them. So it is not representing reals, it is a fixed point number. But when you have more general programs where you are adding and doing arbitrary operations, there you would get any error that would be coming in like fixed point arithmetic.
Okay.
But as you increase the number of bits, that error reduces.
And also in these flip operations for approximating, for discretizing exponential distributions, is there any loss in?
There's no loss of accuracy there.
Thank you for the very nice talk. So basically, when you discretize your distributions, you basically get the probabilistic program which approximates the output distribution. I was curious, in the case of mixed gamma distributions, can you get some basically formal bound on how far away the output distribution of the new program is from the output distribution of the original program, perhaps as a function of the number of samples?
So it's exact up to the b bit width. So if you take the original continuous and discrete, so I have the commuting diagram there. If you take the distribution and you discretize it, or you go through this other route of bit blasting them and then going there, you get exactly the same distribution.
Mm-hmm.
There is no trade-off to make here.
And compared to the original continuous distribution? Before any discretization?
So compared to this one.
Yes.
So the error would be whatever you would get when you discretize it. It's like how to. So I have. So it would be essentially the error between this distribution and this one. So we haven't. We didn't compute them, but like
All
it
right.
seems.
Okay, thanks.
Should be, yeah.
All right. Thank you very much.
Thank you.
Whoop, 1 second. Your laptop caught the cord. There we go. Oh, that's like the only option.
Test 1, test 2. Test 1, test 2.
Try it, yeah.
Test 1, test 2. Test 1, test 2.
Yep, that's good.
Test 1, test 2.
Yep, you're good. All right. All right. So our second paper is compiling probabilistic programs for variable elimination with information flow. And Jianlin Li is the speaker for this.
Thanks, Chair. Hello, everyone. This is Jianlin. The paper is about compiling probabilistic programs for variable elimination with information flow. This is work in collaboration with Eric and Yijo. Probabilistic programming languages are very powerful tools for statistical modeling and inference. Suppose we have a data set that records a person's heart rate, and the problem is to infer whether the person is walking or running. We can solve this problem with probabilistic programming. The program uses a emission distribution to model how heart rate depends on the state of the person. Running leads to higher heart rate. And the program first samples the initial state of the person. It then performs Bayesian conditioning. It conditions the initial state on emitting the observed heart rate. A step distribution models how the state transitions. If a person is currently running, then they are more likely to be running than walking in the next time step. The program samples the next state of the person and conditions this next state on emitting the next observed heart rate. We repeat this many times, and this gives us a hidden Markov model. By returning the next state, the inference problem is defined as to predict how likely a person is running at the next time step, given a history of observed heart rates. We can write this hidden Markov model much more concisely with recursion. And this recursive function HMM takes the initial state and the history of the observed data as input. It then pattern matches on the data and recursively calls itself. We fed these programs to existing PPLs for exact inference. And these PPLs are designed for such programs. We discovered that for HMM of just length 60, it already takes this PPL like tens of minutes to either compile the program or run the compiled program. In this work, we tackle this problem of scalable inference for such probabilistic programs. We work with an expressive functional language with recursion, which allows easy and concise modeling. And we call this PPL Maple. Our compiler for Maple is able to compile a recursive probabilistic program like HMM into a recursive but pure program by factorization and marginalization. We aim for correct compilation, scalable compilation, and also scalable inference on the compiled program. To start simple, let's think about how we solve the non-recursive version of the HMM. To compute the conditional distribution, we need to compute the joint probability of the observed data and the next state. This joint probability is a marginal probability. It marginalizes out the hidden state variables from Z0 to Zn. The joint probability of all the variables can be written as a sequence of factors. Each factor corresponds to one line in the program. Directly computing the sum over all variables is expensive, and the inner product contains n+1 free variables. So computing the sum amounts to enumerating all possible assignments to the latent variables and computing a probability table of an exponential number of rows. So enumeration-based inference doesn't scale. A more intelligent way to do this computation is by factorization and eliminating variables one at a time. We can first factorize the joint probability into two parts. One part contains factors dependent on Z0, and the other part contains factors independent of Z0. We can then push the summation over Z0 inside. And now we examine the inner product again, this time factorizing it over Z1 and push the summation over Z1 inside. And we do this factorization and rearrangement for all latent variables. The product inside each summation contains two free variables. So we need to compute a probability table of 4 rows for each summation. The overall computation is now decomposed into memoizable subproblems, and the time complexity is therefore linear in the problem size. Such an algorithm is known as variable elimination in the land of probabilistic graphical models. Now, what does this tell us about compiling probabilistic programs? In Maple, factorization takes the form of program partitioning. To eliminate a variable, say Z0, the program can be split into two partitions. One partition's probabilistic set effect depend on Z0, and the other partition's effect do not. The first partition's effect can be compiled away, giving rise to a pure expression that is a sum over Z0. And the original program is then transformed by combining the pure expression with the second partition. The resulting program is then partitioned again, this time over Z1. And the compiler eliminates Z1, compiling relevant probabilistic computations into pure expressions. And this process repeats until all variables have been eliminated, at which point we have a pure program. This pure program recovers the desired linear time computation. And the question is then, how does the compiler know which term goes to which partition? And our answer is information flow typing. Information flow typing is an end-to-end mechanism for program dependence analysis. We adapt this idea to probabilistic programs. To eliminate Z0, the compiler labels it high. The requirement is that high information not flow into low information, while low information can flow freely. Here, the compiler infers the typing for all the variables and terms. Terms typed high go to the high partition, and those typed low go to the low partition. Information in Z0 does not flow into the low partition. It is worth looking at the variable binding Z1 in detail. It may be surprising that the right-hand side term is typed high, whereas the left-hand side variable Z1 is low. Doesn't information flow from the right to the left? The answer is yes and no. It's a yes because information does flow from the right-hand side term to the distribution Z1 is drawn from. It's a no because, as we will see, the value of Z1 in a given execution trace contributes 0 information to the semantics of the program. This design of the type system is crucial for program partitioning because otherwise, all the latent variable, Z1, Z2, and so forth, would be labeled high, causing the entire program to be partitioned to high. One way to look at this design is that in Maple, the meaning of a term represented by a distribution over the values the term computes. And so the information flow label of the term classifies the distribution. Consider the typing rule for a variable binding construct. It binds x to T1 in T2. We can contrast it with a Euro information flow type system. What is un-Euro about Maple is that the left-hand side variable x is allowed to be at low, even when the right-hand side term T1 is at high. But why is that? The distribution denoting the composed term is obtained by marginalizing x out with respect to the distribution denoting T1. So this distribution denoting the composed term contains at least as much information as these two terms being composed. That's why in the conclusion of the typing rule, T1's label L1 is conjoined with T2's label. The label of x doesn't matter really. What matters is that the information contained in T1 is tracked in the type of the composed term. This suggests that we can safely type x at low without sacrificing soundness. We prove a soundness theorem for information flow typing. Soundness means non-interference. In the context of probabilistic programs, we interpret non-interference to mean low-labeled computation behaves irrespective of high-labeled input measured theoretically. We prove this non-interference theorem using a logical relations argument. Up to this point, we have been working with the straight-line programs. We also wanted to compile functions like HMM, which uses branching and recursion. We compile them in continuation pathing style. The compiled function takes an extra argument k. K is now the entire continuation. K is the portion of the continuation that the function returns value flows to. It's a pure computation. It represents the probabilistic effect performed by that partition of the continuation. The function body is then transformed with the continuation k, which amounts to compiling the two branches with k. The empty list branch is immediately turned into a pure expression. For the other branch, further translation is needed. We first eliminate variable z. We split the computation into two partitions over z using information flow typing. The high partition is turned into a pure expression. Now we eliminate y, which is the result of a recursive call. So we need to apply information typing to split the continuation of the function call. In this case, we only have a high partition, and the low partition is empty. We create a continuation argument k prime with this high partition, rearrange this computation, and pass k prime to the recursive function call. Now, all probabilistic side effects have been eliminated, and we obtain the pure function as desired. This pure computation computes the marginal likelihood of the original probabilistic computation. We prove that the compilation is correct with respect to this notion of semantic preservation. The theorem is a consequence of the non-interference property of the information flow type system. Now that compilation is proved correct, we assess if compilation and inference scale. For compilation time, we compare Succinct and Maple. Succinct is a state-of-the-art approach to variable elimination. It is designed for the STEM PPL. It enables STEM programs to have discrete latent variables. We use a hidden Markov model as a benchmark. This is a non-recursive program, as Succinct does not support recursion. So the program size increases as the problem size increases. And as a result, we observe compilation time increases as problem size increases for both Succinct and Maple, although Maple's compilation time is much less extravagant. Maple can additionally handle the recursive HMM. The program size does not change with the problem size. So Maple's compilation time scales perfectly. For exact inference, we compare Purple and Maple. Purple features exact inference for recursive programs. We use HMM and also a probabilistic context-free grammar as benchmarks. We observe that Maple is able to recover the polynomial time dynamic programming algorithms invented for such models. Variable elimination is an exact inference method. We can combine it with approximate inference to tackle programs that contains both discrete and continuous variables. By eliminating discrete variables, the Maple compiler reduces the dimension of latent space and may even decompose it into very low dimensional subproblems that can be easily solved by approximate inference. We mentioned two limitations of Maple. First, it supports recursion, but recursion must always terminate. This is in contrast to Purple, which supports non-terminating programs. Second, Maple exploits the topological structure of a model, but not its local structure. This is contrast to DICE, which taps into a program's local structure. Addressing these limitations is interesting directions for future research. To conclude, we have presented a compiler for Maple that uses information flow typing for variable elimination. And the payoff is that Maple allows useful recursive models to be expressed in a functional and recursive style, while enabling sound and scalable inference for a broad class of these programs. And thank you so much for your attention.
All right, thank you very much. We have time for a few questions.
Thanks for the really great talk. When you were mentioning the recursion must always terminate, does that mean it has to terminate in every possible path, or are almost always terminating programs okay?
Unfortunately, it has to be terminating all possible executions.
Cool. And can you give some intuition for what goes wrong in the right? Is it just that you end up needing infinite sums essentially in the unbounded case?
Yeah, exactly the case. Okay. So our compiler doesn't crash. It still compiles to a pure program, and that pure program makes unbounded, non-terminating recursive function calls.
Got it. Thanks. Can I ask one other
Go
question?
ahead.
In the case of sort of partially compiling away discrete variables from continuous programs, what does the type of your translation look like in that case? You still compile to a probabilistic program?
Pardon, what's your question? Eliminating continuous variables?
Or you showed a slide about taking a program with both discrete and continuous variables and eliminating some of the discrete variables.
Yeah.
Right? So does your program transformation in that case compile a probabilistic program to another probabilistic program rather than to a pure program?
So in this talk, we don't have in the motivating example, this HMM program.
Yes, there's no continue. Was that future work, the slide about the LDA and?
Actually, we can. Yeah, I think this slide is the best place to talk about this issue. So we do have some other benchmarks that contains continuous latent variables, and we can also, and the factorization splitting information flow typing also works for continuous ones. It's just they are eliminated. The subproblem for these continuous subproblems are solved in a different way. And here we can use, it depends on the problem. We can use important sampling, AAIS, or other approximate inference method to solve that continuous subproblems.
But does the transformed program contain those algorithms in it, or how does that work?
Yeah, the compiled program do contains a slice of probabilistic computation as a subprogram.
Cool. Thank you.
Yeah, thanks.
All right, thanks. Let's thank our speaker again.
This?
Mm-hmm.
Okay.
That's good. All right, and then we're not yet. All right, our next talk is Equivalence and Similarity Refutation for Probabilistic Programs, and our speaker is Ehsan Goharshadi. And hopefully we can get the slides up. Yes, there we go.
Okay. Hello everyone, welcome to my talk on equivalence and similarity refutation for probabilistic programs. I'm Ehsan Goharshadi, and this is a joint work with Krishan Chatterjee, Petr Novotny, and George Jekilic. So to first introduce our problem, consider the following two programs. The program on the left is trying to send 8 million messages to the other side with failure probability of 1/1000, and the program to the right is trying to send 9 million messages with failure probability of 1/2000. Now, obviously, these two probabilistic programs do not yield the same output distribution after being executed. This is what we mean by these two programs not being equivalent. So when we execute the programs, the output distributions are not the same. And now an interesting question is, given two probabilistic programs, can we prove them to actually not have the same output distribution? And as opposed to non-probabilistic programs, this is a very hard problem because given two non-probabilistic programs, we can simply run them, get the output, and see if the outputs are not the same. But when thinking of probabilistic programs, we need to actually think of these distributions, and reasoning about distributions is much harder. Furthermore, we are also interested in saying, okay, if the programs are not equivalent, then how far apart are they? What is the distance between the distributions that they actually return? To motivate this problem, we can consider two implementations of the same randomized algorithm, for example, where we want them to actually return the same distribution. So it's really important to actually check for, this is actually a way of checking for bugs, for example. Another motivation could be these sampling methods, where these are very familiar, these are very popularized now in the AI and ML community, where they are sampling from a distribution, and now we really need to make sure that the distribution is actually correct in the sampling algorithm. Another very important way to use this is for checking if the probabilistic program compilers are actually doing the right thing, if the compiled program has the same distribution as the actual program. So these all show that actually verification and refutation of equivalence are really important. To now define formally what I mean, consider two probabilistic programs C1 and C2. We say C1 and C2 are output equivalent if for any measurable set B in the possible set of outputs, the density of B in the first program and the second program after termination is the same. And now the equivalence refutation problem asks, given two programs C1 and C2, prove that they are actually not output equivalent. There has been a lot of previous works related to these problems. I'm going to summarize them here. The first class are logical frameworks which are not automated. The second class are methods that actually only consider finite state probabilistic systems. But in the case of programs, we are also very interested in programs with real valued variables, which means we actually need to deal with infinite state programs. And the third class are statistical methods, where they basically sample traces of the program, and then they try to think and infer non-equivalence of programs based on their samples. However, these methods do not have very strong guarantees on the results, so they cannot say for sure that these two programs are not equivalent because they only can see some finite number of traces. And also they don't scale well when the running time of the programs is huge, because they still need to take a lot of samples, and each sample might be large on itself. Our method, on the other hand, is the first one, which is fully automated. It supports infinite state programs with real valued variables. It has formal guarantees on its results, and it's a static analysis method, which means it actually does not depend on the running time of the program. All right, so I'm now going to dive into our proof rule for disproving equivalence. Our proof rule on a high level is basically searching for a function f from the possible set of outputs of the program to the reals, where the expected value of f upon termination in the first program is not the same as the expected value of f upon termination in the second program. Equivalently, we can only search for a function f where the expected value in the first program is less than the second program. And this means we can also only look for an upper bound for the expected value of f in the first program, which is less than the expected value of f in the second program. In the paper, we show that this is actually a sound and complete proof rule for disproving equivalence. So if two probabilistic programs are really not equivalent, such a proof rule for them has to exist. Now for the upper bound part, so now our goal is to basically find this upper bound and the lower bound. For the upper bound part, we introduce the notion of upper expectation supermartingales, or for short UESMs, which is a function from the states of the program to real variables. And it should satisfy two conditions. First, it should be 0 on output, so on every reachable termination location, its value has to be 0. And second, it has to satisfy an expected f decrease condition, which means for every state s of the program, the difference between the current value of u and the expected next value of u should be greater than the change in function f. Now, intuitively speaking, this function u at each state s will be an upper bound on the expected difference between the current value of f at that state s and the value of f upon termination, which means specifically in the initial state of the program, the sum of u and f will be an upper bound on the value of f upon termination of the program. So by having a UESM, we have an upper bound for the value of f at termination. Similarly, for lower bounds, we introduce the notion of lower expectation submartingales, which is again a function from state of a program to the reals. It should be 0 on output, but here it should satisfy an expected f increase condition, which means the expected difference in the value of L should be less than or equal to the expected difference in the value of f. Then again, intuitively speaking, L at each state S will be a lower bound on the expected difference between the current value of f and the value of f upon termination. So in the initial state, the sum of L and f will be a lower bound for the value of f at the end. So our complete proof rule will look something like this. A function f from the possible outputs to the reals, a UESM u for the first program, an LESM L for the second program, such that the sum of the u and f in the first program is less than the sum of L and f in the second program, which means the upper bound we have for f is less than the lower bound for f in the second program. In the paper, we show 4 conditions where under each of them, this proof rule will actually be sound for disproving equivalence. First one is if the program has statically bounded termination time. So if there is some number n where we can say the program is definitely terminating after n steps. Secondly is if the program has statically bounded variables, which means all variables are bounded from above and from below. There are also 2 other conditions which are complex, and I'm not presenting them here for the sake of time. Algorithmically speaking, we also come up with a template-based synthesis algorithm for finding these proof rules. It has 4 steps. The first step is basically fixing a symbolic template for all the parts of our proof rule for the function f, the UESMU, and the LSML. Then we collect their defining constraints, which are of the form, okay, there exists some valuation of a template variables such that if some condition is satisfied, something else should be satisfied. Just trust me, they look like this. Then we use Handelman's theorem from algebraic geometry to convert these exist for all conditions into purely existential linear constraints. And then we simply solve the linear constraints with the added constraint that the sum of u and f at the initial set in the first program should be less than the second program. For example, consider the first program that I showed. We first fixed these templates for the functions f, u, and l. So here you can see that we put the template s1 plus s2 fail plus s3 send, where s1, s2, and s3 are unknown template variables. We are looking for valuations of this s1, s2, s3, and also these c variables for u and d variables for l. We are looking for evaluation of these variables such that it satisfies the 0 on output and the f increase, f decrease conditions. Now, applying our algorithm and feeding the linear program to a solver like Urobi, we obtain this witness for this program, which basically means that the expected value of sent minus fail in the first program is different, or is basically less than the value of sent minus fail in the second program. So in the title, we were also talking about similarity, which is basically how far are these two programs from each other. So the problem that we consider here is given two programs C1 and C2, we want to find the contour-Wish distance between their output distributions. We want to find a lower bound here to be at least epsilon. And in the paper, we have come up with a similar proof rule for refuting similarity. And we have also come up with a very similar algorithm to make it fully automated. So if you're interested, you can read our paper. Experimentally speaking, we have gathered 18 loopy programs from the program analysis literature. And as a baseline, we consider a combination of PSI and Mathematica. PSI, as mentioned before, is a symbolic integration method, which given a probabilistic program, it outputs the exact distribution of its outputs. And what we do here is, given two probabilistic programs that we want to prove that they're not equivalent, we feed both of them to PSI, we get their output distributions, and then we give these distributions to Mathematica and ask Mathematica to prove that they are not actually the same distributions. However, PSI only supports statically bounded loops, which is why we had to modify our benchmarks to have loop lengths of lengths 10, 100, and 1000. So we had 18 original benchmarks, and we also have these 3 modifications. We have 72 benchmarks in total. Here is a summary of our experimental results. As you can see, our method can successfully disprove equivalence in almost all the benchmarks, where PSI disproves a lot less. And also our method can find lower bound on the contour-Wish distance of the two programs in almost all cases. And also, you can also check how the times our algorithm is very fast, actually. Here is the rest of the experiments that we did, and you can still see that our algorithm can successfully refute equivalence in actually all benchmarks, while also finding a lower bound on the contour-Wish distance. All right, to sum up, we came up with the first static analysis method for disproving equivalence and similarity of programs, which is fully automated, has formal guarantees on its results, supports infinite state programs, and does not depend on the length of a program executions. And as future works, we are thinking of extending this method to programs with conditioning and observation statements. We already have some preliminary results, but we are still thinking about this. And another very important extension is to extend this to non-polynomial UESM and LESM. So basically, the algorithm that I showed, because we use these theorems from algebraic geometry, we can only look for polynomial witnesses. However, other algorithms to actually consider non-polynomial UESM and LESMs will also be very interesting. To this end, I will look to conclude, and I will be happy to answer your questions.
Let's thank our speaker.
Thank you for the great talk. One question I have is, you said the programs need to satisfy a set of conditions for the soundness to hold. You didn't show all of them. Some of them were maybe more complicated. Can you give a sense how feasible it is to check these conditions from the source code of a program?
So most of them, I would say, can be checked statically again on the program. So for example, checking if a program has statically bounded termination time. There are many methods for proving termination of programs, so they can all be used. Also for statically bounded variables, I think this can be shown as a sort of invariant on the programs. And the third and the fourth method are also, the conditions, they are also pretty much, I mean, there are various methods for checking them. That's why we really did not consider checking them here.
Okay.
But
good.
Yes.
Yeah, and just briefly a second question. Your method searches for polynomial certificates. So do you start with degree 1, degree 2, degree 3, and you're doing a search in that way?
Yes, exactly. So I summarized that part, but the idea is exactly we start with degree 1 polynomials. If we found something, then that's great. If we didn't, we go to degree 2 and then degree 3.
Okay, good. Thank you.
Okay, thank you for a great talk. I have a question. I see the proof rule you provide is sound but not very complete. And I would like to know when the two programs are very close, are your proof rules are enough to resolve this question? Sometimes like the probabilistic parameters is very close, like in this situation, I would like to know your proof rule is enough to resolve.
Yes, so even in our experimental evaluation, I think we had benchmarks where, for example, this Bitcoin mining, the distance between the programs is very small. It's like 0.005, but still our method can find this, because one thing about this equivalence refutation witness that we have is that you can multiply this function f by any constant, by any positive constant, and it will still, and you can basically multiply the whole witness by a positive constant. And it will still satisfy all the conditions. This means even if the distances are very small, you can come up with functions with big enough coefficients such that a solver like Robi can still find it.
Maybe another question is that I would like to know, have you considered the polynomial template? Because I think it's the linear template you use and use the Handelman theorem. Maybe in the polynomial templates case, the Putnam theorem can be used to resolve the template.
Yes, so we also considered polynomial templates, and for polynomials we used Handelman's.
Yeah, I know the Handelman is not enough to resolve the polynomial case.
No, but because in this case, so we can also talk about this offline, but the left-hand side of our constraints are usually linear expressions, and the right-hand side are polynomials. So that's why we can use Handelman, and it still stays sound and complete in this sense.
Okay, thank you.
All right, thank you much.
So I have one question. So can your similarity refutation works also for refuting coupling properties?
What do you mean by coupling properties?
I mean, there is a coupling between two programs so that their outcome distribution are close.
I think they should be able to. We should be able to use them for that too. Yes.
Okay. Thank you.
All right. That like there. is it probably mirrored? Yeah. All right, our next talk is GenSQL. What's a probabilistic programming system for querying generative models of database tables. And our speaker is Matthew Hua. Take it away.
Thanks so much. Hi everyone, I'm Mathieu. I'm a research scientist at MIT. Today I'll be presenting our new system, GenSQL. This is joint work with all of these wonderful people at MIT, CMU, and Digital Garage. Before explaining what the language is, let me give you some context for this work. So this table is an extract from the Stack Overflow 2019's developer survey. Each row represents a developer who answered the survey. And each column has an attribute such as a programming language that they know well or not, their aspiration to become managers, or whether the income is above a certain threshold. Given this data, I may ask, what language should I learn to maximize my chance of raising my salary more than 10K? Or what if I could learn 2 languages? I could also ask, what's a probability that you're underpaid given your skills? Or even ask questions about equity. What languages probably have the biggest gender gap? With what confidence can we say this? Our system, GenSQL, allows us to answer such questions by running queries against a predict model of the data. The high-level vision for the work that it builds towards is, what if every database came with an AI domain expert? More specifically, how can we leverage generative predict models to answer a variety of queries in an accessible way that doesn't always require expert knowledge in either predict programming or statistics? In this work, we propose an extension to SQL to make it accessible to a large number of users to query predict models of their data, answer a variety of questions ranging from imputation to prediction or synthetic data generation or anomaly detection. Given a generative model that satisfies our model API, the user only needs to know a few keywords to start writing interesting queries. And you may wonder, why SQL? Well, right behind Python, which benefits from many libraries, but kind of act as a jack of all trades regarding data processing, SQL is an easy-to-learn declarative DSL and the second most used language for data science. So specifically in this work, we designed the GenSQL language, an instantial that allows to create generative models and specializes to tabular data. We propose a unifying interface that generative models have to satisfy to be queryable by the language, offering a separation of concerns between model building and model querying. This high-level declarative language is lowered to queries on the data and model API. We give additional semantics to the high-level language and low-level language, and prove soundness theorem, depending on whether the model satisfies an exact or approximately the API. We can prove different guarantees for the output of queries. We provide an open source implementation of GenSQL enclosure. And we tested our system with 2 case studies using real-world data, performance evaluation, code comparison, and evaluation of our optimizations. OK, so that's a high-level view. But what does the language actually look like? So on top of SQL construct, we have 4 main new constructs that allow to query generative models in conjunction with querying data. The generate query allows to generate synthetic data where each sample model represents a synthetic row. The given clause is the analog for model to filter on data. Instead of filtering out the rows which don't satisfy a certain predicate, it constrains the model to generate data that satisfy the predicate. And the constraint model is just another model, so you can nest given queries. The probability of clause evaluates the likelihood of an event under the model. It can, for instance, be used in a select clause, as the example on the left. To loop over the data and evaluate the likelihood of a specific set of attributes per row, looping over all the rows. This can, for instance, be used for anomaly detection. And finally, the generative join construct is a sort of mixed join. So more specifically, it loops over the rows of the data, and for each row, computes a synthetic row generating from the model, which can be conditioned on specific values on that row. That can be used, for instance, to do sensible data imputation or data prediction. Given the values on the row, what's a sensible value to put in a new column? What's a good prediction for a new column? So that's all fine in theory, but what does it actually look like on some example? So first, using a model from the Stack Overflow 2090 data, using the generate keyword, we can get synthetic rows that would look something like this. If instead we condition the model on developers who know enclosure using the given clause, then the produced rows would look something like this. Now we could estimate probabilities by generating synthetic data and counting in a sort of very simple way, but we can do better and directly ask the probabilistic model to compute probabilities. These probabilities represent the belief of a certain model about an event. So while one model represents a distribution and returns one number for a probability evaluation, we can also use a variety of models. For example, different synthesized model to evaluate the same event and get a sense of inferential uncertainty of how confident we can be about these estimations. For instance, evaluating the probability that you use Emacs, if you know closure at a different model, we'd get a distribution that could look something like this. And likewise, if you're evaluating the probability that your salary is over 130K, if you know closure. The language also enables nested queries, which can be used to construct complex queries. As a sort of simple example, we could first generate synthetic data using a record synthesizer, call the resulting table synthetic data, then loop over this table, selecting a specific attribute age, and computing the probability of a certain attribute, again, per row, under another model. This is a high-level schematic of the query processor, which takes some GenSQL query, eventually producing results. It starts with query in what we call the permissive syntax, which allows some conveniences and syntactic sugar, such as the example on the top. Then some inference is automatically performed when going from a permissive to a strict syntax, which helps with conciseness, accessibility, and reducing errors. So this is, for example, the difference, where we infer that in the given statement, we're looping over the developer salary information per row. Now the query is then turned into a query plan, optimized, and then finally obtaining results. Here's another example of like a one-line generative query for conditional synthetic generation on the iris dataset. And we can compare this to another system here, for example, scikit-learn in Python. And well, even though the implementation contains data loading and pre-processing, model building, and a few comments, just the model creating part is more than 50 lines and error-prone. So in addition, scikit-learn doesn't really provide a good mechanism for constructing models and conditioning them. So compared to this, the GenSQL query strikes by its simplicity. So far, we already assumed we had access to a generative model that we could query. But it turns out that plenty of models from the literature can be used by our system or combined together and then used. So examples are, for example, generalized linear models from statistics, particular generative neural net architectures such as CTGAN from AI. We can leverage probabilistic database, work from the probabilistic database literature, or design custom distribution manually using a probabilistic programming language. But maybe for us, more importantly, another source of probabilistic program is obtained using structural learning. In fact, GenSQL uses one of these algorithms as a default backend, which is used in the majority of our experiments. So by Bayesian structural learning, I mean a form of probabilistic program synthesis. Given real data, we obtain probabilistic programs that can serve as generative model of the data. So here we use a variant of Crosscat from Masinka and colleagues, which builds a partition of the column, then partitions the column, in each partition partitions a row, and then infers cluster-specific parameters for each partition. But instead, we can visualize it in something in the following way. So on the right, we're showing data streaming in one row at a time. On the left, we're showing a schematic of the uncertainty in a structural learning algorithm over the structure of Posterior program at multiple levels of detail. As more data is added, the algorithm builds a richer picture of the world. Final details in the structure begin to resolve. The produced Posterior models are compatible with SPPL from SATA colleagues, which is a Posterior program supporting exact inference. So these produced baseline models actually capture the interaction in the data. For instance, when looking at synthetic data, if we look at tuples of columns, the frequencies of the tuples of attributes are respected, comparing observed to generating ones. In addition, as shown in an earlier version of the system, we can override the default model with custom code representing expert knowledge to improve prediction. In this particular example, we have a data set containing various information about satellites, and we can predict what the period should be as a function of apogee and perigee using Kepler's laws from physics, which can write as a little Posterior program in, for example, Gen, that overrides part of the default model. So we've just seen a diverse way to obtain generative models to be queried by GenSQL, and I now show how to use GenSQL on real-world data. So first, some context for these two case studies. So we look at two scenarios, a wet lab experiment in synthetic biology, where the kind of questions scientists have could be, what is the probability that modifying gene X won't influence any other genes? So in this case, real data acquisition can be quite costly, and researchers are interested in understanding and analyzing the data. So having accurate synthetic data can be tremendously helpful in these cases. Secondly, in medicine, researchers are interested in anomaly detection in clinical trials. For instance, they would like to detect performance issues or data entry errors or variation of criteria, and I kind of give like informal kind of examples you could be looking for. And in this case, it can also be helpful to have access to a Posterior model one can query and be able to design custom logic for what a probable anomaly is. So for the first case, on the left, we have two GenSQL queries, one setting real data, which is sort of the black dots on the right, and the second one showing generating synthetic data in orange on the plots. This particular data set from an experiment testing genetic circuits from Nielsen and colleagues, and the plots are from the overall population. We can also show plots when we add substances such as IPTG or Robinos, whatever that is. In all these cases, we're able to produce accurate synthetic data. And we can compare the synthetic data obtained from different backends. So on top, we use a baseline using SPPL, obtained from structural learning. The second and third one are GLM and CQGAN, which are classically used in this field for the ease of use. So as we can see, the one using a Posterior programming language produces much better synthetic data. For the second case study, we look at data from the BEAT-19 clinical trial, which contain data about COVID-19 and records behavior, environment, variables, and treatments. So here, we design a custom logic for anomaly detection by looking for rows with improbable BMI, given the rest of the values. So we eliminate overall extreme BMI values, so the values that we found are not extreme, they're just odd or strange given the rest of the contents of the rows. So in this particular case, we find 8 participants with BMI above 30, which is high, although they all report to be exercising and having above average or well above average health. And we can plot these values to get a better sense of the rows found to be anomalous. Let me also show you a couple of performance benchmarks. So we compare GenSQL to Scholar's competitor BaseDB, which is well optimized and tailored for the specific structural learning algorithm backend it's attached to. We find that GenSQL is about 1.7 to 6.8 times faster, in part due to our implementation being in Clojure, and also thanks to optimization. The produced backend models are compatible with SPPL, which we can leverage to answer conditional probability evaluation with zero variance, as SPPL is exact, while BaseDB resorts to rejection sampling in these cases. We also test the optimization. And first, we see that there's like a 1.1 to 1.7 overhead of the query language compared to manual implementation in full closure. But the effect of optimization can drastically help with performance. And after these examples and evaluation, I want to say a few things about our formalism. So to begin with, we formalize GenSQL as a simply typed language extending SQL. On the left, we have classic SQL expressions, such as join and select. On the right, we have parametric extension, so generate and generative join. We can construct models, either loaded from memory or using the given clause to construct condition models. Scalar expression typically represent operation in a select clause, such as data.age, something like that. On the operating side, we have priority of expressions, which as argument take what we call an event, which is a restricted class of expression that encode either a specific value or interval constraints. As said at the very beginning, our formalization is as a typed language, where the type system ensures restriction for queries to be well-formed and have a clear semantics. For instance, it disallows to condition on a model variable twice on different values, such as given x equals 7 and x equals 8, which wouldn't really make sense. The high-level GenSQL language is lowered via a program transformation T to a kind of simply typed lambda calculus with primitive for the model API methods. We give semantics to the high-level one and the low-level one. The high-level one is using measure theory, and if you're into advanced semantics, it's using something akin to the point process monad to present table as random set of rows. And depending on, again, whether the models satisfy exactly or approximately the methods, we have two semantics, which are linked to the high-level semantic by different logical relations. As a quick example, here's a semantic for a generate query in environment gamma delta. We first evaluate in environment the number of rows we want to produce. Then we evaluate the model. Again, it can be a condition model that depends variable from the local environment. Then we sample n independent times from the model and return the union of these rows. Many classes of generative models will satisfy a version of the model, but we specifically show in a paper how SPPL and triggered multivariate Gaussian satisfies the exact API, while ancestral sampling, as is present in several general purpose SPPL for approximate inference, satisfies a weaker guarantee of strong consistency. And I'll say just a few words about optimization. This mixed workload of query processing or programming comes with interesting questions regarding the design of optimization. Cross-optimization become available, such as the following, which benefit from the fact that a typical query involves many calls for a basic program. So we can cache results and simplify queries sometimes. But there's also queries which are reusable from the database literature and which are not valid anymore when we add randomness to the picture. Quick example, if we want a certain query that looks at data, that looks at a model where in each cluster the variables are independent, we can leverage this structure to simplify the query. While a traditional join optimization like here would not be valid because it introduces undesired correlation in the result of the query. So this concludes a brief highlight of some of the formulas we did in the paper. Finally, here's some items that we present in our paper. And current work at MIT has been field testing this approach with companies such as Takeda Pharmaceutical, Liberty Mutual Insurance, and City Consumer Data with Digital Garage, and incubating a startup based on this new kind of AI expert system. It's also exploring scaling structural learning, for instance, leveraging GPU computation and exploring LLM generation for GenSQL from English. Leveraging the large body of SQL already in the training dataset for modern co-tuned LLMs. Here we're seeing a system answering questions in English about salary inequity in the US software industry, identifying individual developers who are probably underpaid and aggregating by gender identity to get a microscopic picture. Over time, we hope that GenSQL makes this kind of predictive reasoning widespread anywhere there's like data available for a SQL database. And finally, we see some avenue for future direction where the model API allows a separation of concern between model design and model querying, analogous to Code's design, advocating for the separation of query from physical representation memory. And we also have interesting question. I'm happy to talk to you more offline about for engineers or designing new PPL specialized for this workload. And there's interesting math also in the paper that I invite you to look at if you or talk to me if you're interested.
All right, thank you very much. Unfortunately, we do not have time for questions on this one, but we'll go right into the next talk. Definitely invite people to contact the author offline.
Hello. Hi.
All right, looks like we're ready. Okay, so for our last talk, we have probabilistic programming with programmable variational inference. And our speaker is Becker McCoy. Looking forward to this, thank you.
Are you getting any? Great. Cool. Hi, everyone. I'm McCoy. Today I'll be discussing some joint work with my co-author, Alex Lev, lab members from the Probabilistic Computing Project, Martin Renard, and my advisor, Vikash Mansinka, investigating the operations involved in variational inference and how to automate them efficiently for probabilistic programming languages. Probabilistic programming languages are an emerging class of systems which aim to support practitioners of probabilistic modeling and inference. These systems provide automation to help users write down and work with probability distributions. One key operation is conditioning, which arises repeatedly in Bayesian inference, a model of reasoning that represents many processes in machine learning. To support Bayesian inference, probabilistic programming languages provide two key capabilities. The first capability is the ability to describe joint probability distributions, which probabilistic programming languages automate by providing expressive modeling languages. Using these modeling languages, users can write down probability distributions as programs, which often make use of other complex programs like 3D renders or symbolic planners or program interpreters as part of their definition. The second capability PPLs provide is inference libraries, automation which supports approximate inference algorithms designed to provide approximate representations of the conditional distributions induced on the programs written in the modeling languages. PPLs support two main workhorse families of approximate inference algorithms, Monte Carlo methods and variational inference. Monte Carlo methods have received extensive coverage in PPLs, boasting advanced automation, modular implementation strategies, and formal semantics covering the full pipeline from user programs down to inference code. Several PPLs also make it easy to extend their Monte Carlo libraries with new algorithms. In contrast, although there are some great systems supporting common variational inference workflows and some great pioneering PL work addressing key aspects of the semantics and correctness of variational inference lacks an end-to-end formalization, and variational inference features tend to be less modular with complex implementations that interleave many concerns. The goal of our work in this paper is to find a more modular, programmable approach to implementing variational inference in a probabilistic programming language that can express a really broad array of variational inference workflows. I'll start by telling you about some of the technical challenges in providing such a treatment towards variational inference. What makes variational inference hard? Fundamentally, variational inference problems are optimization problems. Whereas Monte Carlo methods are about sampling from a distribution, variational inference is about optimizing the parameters of probability distributions. The objective functions f that people optimize in variational inference are quite complex. And the key challenge in implementing variational inference is finding some way to compute or estimate their gradients. Unlike the typical optimization objectives found in machine learning, these variational objectives are defined in terms of integrals and density functions of probabilistic programs. And we can't just run standard AD, standard automatic differentiation. Existing probabilistic programming languages have a lot of specialized machinery for estimating gradients of one or two commonly used objectives F. But what we really want is a system that is expressive, working for as many choices of P, Q, and F as possible. We want a system that is scalable. System complexity should scale gracefully as we incorporate new language features or new gradient estimation techniques. And we want something that's easy to reason clearly about. To address these challenges, we contribute a new modular approach to variational inference. Our approach is based on a decomposition of the concerns of variational inference into two languages and a set of program transformations. Our approach offers automation which confronts the technical challenges of variational inference along three key axes. Our approach is expressive, meaning it supports a large space of P's, Q's, and F's. We support a large space of P's and Q's by providing a high-level generative probabilistic programming language called Lambda Gen, with support for expressive probabilistic programming features like tracing and stochastic control flow. Users can utilize this language to author their own model and variational approximation programs, these P's and Q's I was just talking about. To support the space of variational objective functions, we expose a differentiable probabilistic programming language called Lambda Addev. This language can make use of the P's and Q's, which users write in the generative language, by utilizing program transformations which implement sampling and density evaluation for P and Q programs in terms of this differentiable language. F programs constructed in the differentiable language can automatically receive unbiased gradient estimation support. Our approach is also formalizable, and we present a denotational semantics for our entire language automation. We utilize our semantics to state a soundness theorem which characterizes the conditions under which our automation produces correct unbiased gradient estimators. And we provide an inductive logical relations argument for our theorem. In fact, our semantics and theorems are modularly extensible, and I'll discuss that later in the talk. We also contribute a GPU-accelerated implementation of our approach, a new system called GenJAX VI, which implements our automation in JAX, a Python-based array programming system with JIT compilation, user-directed parallelism, and good support for automatic differentiation. To evaluate our approach empirically, we studied the expressiveness and performance of our implementation on several variational inference algorithms from the deep learning literature. So we've discussed the technical challenges of variational inference in the abstract and how we believe our approach addresses them. To concretize the discussion, I'm going to turn to a tutorial example to highlight the features of our approach. Variational inference algorithms begin life with a model program, what I've referred to as P before. The user starts by writing one of these model probabilistic programs. This program samples x, y, and z coordinates near a cone by first sampling an x and a y, figuring out how high up z should be, and adding some noise to that. Samples from this program are shown in this figure on the right. An inference problem occurs when the user wants to solve something like this. If I tell you z, what might x and y be? For instance, if I tell you that z is equal to 5, you might think x and y are probably somewhere near this circle of radius square root 5. To encode this problem in our language, we change this sample statement for z into an observe statement that observes the value sampled from the normal distribution to be equal to 5. In variational inference, the way we answer the question, what might x and y be, is with another probabilistic program, which approximates the posterior distribution over x and y given that z is equal to 5. We write down the form of our approximate posterior as a program. These programs represent families of approximations called variational approximations. The program itself is often called a guide program in the variational inference literature. In this talk, I'll refer to these programs as Q programs. Q is a program which takes parameters as input, and as we vary the parameters, it encodes a different distribution on x and y. Here's one example of a Q program, this program called Gaussian family. In this program, the parameters control the location and scale of a bivariate Gaussian. On the right-hand side, I'm showing samples from this untrained program, just this prior. Variational inference algorithms try to find the parameters that make Q phi look as close as possible to the posterior. In existing PPLs, we would write down our P and Q like this, and then run automated variational inference. This animation on the lower right is showing the process of gradient descent as the Gaussian's parameters are fit to the inference problem at hand. Unfortunately, the learned approximation is not very good. That's because this particular objective function, the evidence lower bound, or ELBO for short, encourages Q to nestle itself within a mode of P, not to cover all of P's modes. There are potentially other objective functions we could use here that would lead to different results, but each different objective function requires different logic for estimating gradients, and in existing systems, supporting new objective functions requires going in manually to the system backend and making really non-trivial edits. In our work, we instead give the probabilistic programmer access to the full expressiveness of the underlying math of variational inference. They write their model as a probabilistic program. They write their variational family as another probabilistic program. They write the variational objective as a third probabilistic program. Rather than optimize a fixed objective like the ELBO, we treat the objective to optimize as an input expressed by the user as a short program in an expressive differentiable language. To do variational inference, we need to automatically generate fast code implementing the gradient estimator given the objective model and variational family. To do this, we have three separate program transformations that together provide the necessary automation. The first two translate the user probabilistic programs into routines for density computation and traced simulation, which can be invoked by the user's objective program to define the objective to optimize. The third transformation compositionally estimates gradients of the user's objective. This modular design makes it possible to extend our system locally with new language features or new gradient estimation strategies, just by explaining how each program transformation should apply to the new feature. What does this mean for users? First, if the user does want the standard push-button behavior, that just corresponds to a 4-line variational objective that we provide as a library function. Note how the code defining the objective can use various specialized constructs like the expectation operator or the simulation and density operations that can be applied to the model or variational family. But the user can also change the objective function and get qualitatively different results. For example, this objective is called the importance-weighted ELBO. I'm showing that on the right-hand side. And it places less pressure on the variational family to stay completely within one mode. Our framework automatically estimates gradients of this new objective, allowing the training loop you see animated here. One way of understanding this objective is that it optimizes the variational family to be a good proposal distribution for importance sampling. And indeed, on the lower right-hand side, the lower right-hand animation, I'm showing the results of importance sampling with the learn proposal from the left-hand animation. One final strategy we might employ towards solving this problem is to change the Q program, our guide program, by including more logic to capture some intuition we might have about what the posterior looks like. Here we've changed our Gaussian family to a better family, which samples a random angle first, and then jumps to a point on a circle of radius r described by that angle before sampling from normals near that point. And I'm showing some samples here on the lower right-hand side. One problem with this Q is that it samples an extra auxiliary random variable, the angle v. If we attempted to use the normal ELBO with this guide, this extra auxiliary random choice would disrupt the optimization. If we instead use the marginal distribution of better family over x and y, we recover a family of variational inference algorithms called hierarchical variational inference, or HVI for short. Training with this variational inference algorithm leads to the fit on the lower, in the lower right-hand animation. Okay, we've evaluated our approach. On larger scale examples from deep learning. Let's now look at a model called AIR that was influential in the early days of probabilistic deep learning. In this example, the goal is to learn a generative model of a data set of images. These images can contain multiple objects, and each object can have a unique pose in the image. Here I'm showing a few example images from a data set called multi-MNIST, just images with multiple MNIST digits. Like before, we are going to approach this task with a P and a Q program. Note here that P also has learnable parameters, not just Q. Variational inference also captures settings where one wishes to learn the model P from data. Now, the idea for the P program is that we're going to write down a probabilistic program which represents our prior beliefs about how many objects are in the scene, and their locations and style. For each object, the P program will sample a sub-image at the location using a distribution that's parameterized by a neural network over the style. Now, the idea for the Q program is that we're going to look at the image and attempt to guess how many objects are in it, where those objects are located, and what the style of the object is. The style of the object is, again, encoded by a neural network embedding. The goal of training is to find a P program which represents a good prior that captures the features of the data set, the number of objects and where objects are likely to be placed, as well as what they tend to look like. And to find a Q program which, given an image, can identify the number of objects in the image, where they are placed, and what their style is. After training, the Q program can be used for segmentation, to take an image and identify where the objects are, and P can be used to generate images in the style of the data set. When this model, AIR, was presented at NeurIPS in 2016, it made quite a splash and has been cited around 500 times. However, the data-efficient design of AIR didn't become mainstream for image generation. Training these models is significantly more challenging than training transformers because of the discrete latent variables. TensorFlow and PyTorch don't automate Monte Carlo gradient estimation strategies needed to get good performance with discrete latent variables in the probability distributions. We found that our approach significantly improves the speed of training for these architectures and also automates a much broader class of algorithms. This opens up a new route to scaling for a much broader family of deep learning models than TensorFlow or PyTorch alone. Let's use this model, AIR, to evaluate our approach's gains in expressiveness, automation, and speed. Here I'm showing you a table. It turns out there are lots of different ways to train the AIR model. You can make different choices of the objective function and also different choices of the gradient estimators for the random choices in the Q program. Each row of this table is a point in that combinatorial space. Existing systems support a handful of these options, but our modular approach can automate all of them. Many of them have never been explored for AIR or for similar models. Why does that matter? Well, we can now easily explore the space of options and see what works best. We did that. Here's a plot comparing a bunch of different approaches to training AIR. The top plot shows the loss curves and the bottom plot measures accuracy on the task of identifying how many digits are in a given image. It's worth noting a couple things. First of all, different points in the space really do have significantly different performance characteristics. Our fastest algorithms are 5 to 10 times faster than the slowest. Second, the fastest training algorithms for AIR in our experiments are the ones that are not supported by existing systems and have not been previously applied to AIR. These algorithms are the gold-colored lines in each of the plots. These were the best estimators across the entire suite of estimators we tried in terms of wall clock time until convergence. To better understand the performance characteristics of our implementation, we also consider the training time to complete a single epoch of training in our system and in Pyro. Here's a plot which compares equivalent estimators. Our system is in blue and Pyro's is in orange. Our implementation estimators are on average 10x faster than Pyro's equivalents. For reference, I'm also showing the estimators corresponding to the new algorithms from the previous slide. These are the elbow MVD and iWelbo MVD columns in this plot, estimators which are not automated by Pyro's automation. Here's an animation of training using one of these new algorithms. On the left-hand side, we show the same objective and accuracy plots from the slide before. On the right-hand side, I'm showing the original image next to the reconstructed image using the AIR model. Each frame in the animation illustrates a different checkpoint in training. At the bottom, I'm showing the wall clock training time. The wall clock time when the AIR paper was first published in 2016 was days to train their model. Now, thanks to hardware and software improvements, Pyro can train AIR in about 20 minutes. With these new algorithms and GenJAX VI implementation, training completes in about 40 seconds on a consumer GPU. Finally, I want to say a bit about how our modular design facilitates formal reasoning. As we discussed, the user needs to bring 3 ingredients to define their VI problem, a P, Q, and F program. Our automation is designed modularly in terms of 3 composable program transformations. We have 1 language for defining probability distributions. That's where the users write their P and Q programs. We formalize this language as a simply typed lambda calculus called lambda gen. We have another language for defining objective functions. We call that language lambda addev. This language has an expectation operator, and we can then introduce 3 program transformations. These transformations are sim, a differentiable simulation transformation, density, a differentiable density evaluation transformation, and addev, a transformation which supports automatic differentiation of expected values in terms of unbiased gradient estimators. I'll quickly describe each of these transformations. Sim takes a lambda gen program and turns it into a lambda addev program that simulates from the distribution and can be used with lambda addev's expectation operator. Density takes in a lambda gen program and turns it into a lambda addev program that computes the density of the distribution described by the program. Addev takes a lambda addev program and turns it into a lambda addev program that unbiasedly estimates derivatives of the original program. These program transformations are each about half a page, defined inductively on the syntax of the source languages and proven correct using logical relations. Here, for instance, is part of our inductive definition for sim. Here's density. And here's the additive transformation. Once we have the transformations, an overall correctness theorem can be established. The first such proof that really goes all the way from the source program through tracing and automatic differentiation and the implementation of gradient estimators all the way to an unbiasedness result. Adding a new feature to lambda gen and extending our formalization just requires modularly extending these transformations and adding one new case to the proof. Furthermore, the three transformations can be separately proven correct. You don't need to reason about the interactions between them. To summarize our contributions, we presented a new modular approach to automating variational inference. Our approach is expressive, formal, and extensible, allowing users of our automation a large amount of design freedom when constructing new variational inference algorithms. In addition, we provide a GPU-accelerated implementation of our approach called GenSQL and show that it supports fast and modular development of variational inference algorithms. Finally, there's an open source artifact with a version of GenSQL to accompany our paper. And that's it. Thank you for listening.
We have time for maybe one question. All right, well then, oh.
Thank you for the nice talk. One question I have is, you have a DSL for specifying these objective functions. Have you thought about ways in which you can provide some type of language support or type system that ensures these objectives are valid? Maybe they're lower bounds on the marginal likelihood or other criteria.
Yeah, there are different criteria that you might want to enforce in terms of validity. One thing that when you're using gradient estimators, almost all unbiased gradient estimators have certain regularity conditions they assume about the cost function that they use. The work that we're building on, this additive paper, has some static analyses for the language it presents for ensuring that these conditions are satisfied so that the unbiased gradient estimators that it constructs are valid gradient estimators. But can you repeat this thing you're asking about?
Regarding the objective. So the user
Yes.
can write their own objectives, is that right?
That's correct.
Right,
Yep.
and in general, we want these objectives to correspond to some type of lower bound on the marginal likelihood.
Right, right.
Is there any sense in which we can, to help the user write an objective which makes sense to optimize?
Yeah, I'm sure there is. We didn't think about it for the paper, but I'm excited to think about it, and yeah, I'd love to talk more about it.
Great, thank you.
Cool.
All right, thank you. And that concludes our session. Next up is lunch. Reminder, there's lunch upstairs and downstairs.
I'll introduce you. All right, I think we're ready to go. My name's Steve Blackburn, and I'll be chairing this session. I'm at Google and the Australian National University, and our first speaker will be Hongfei Fu, who's at Shanghai Jiaotong, and he's going to talk to us about static posterior inference of Bayesian probabilistic programming via polynomial solving. So thank you, Hongfei.
Guan Li and also Professor Lu Kang. So next, okay. So the background of the research is that we try to write Bayesian models as programs, and then we try to perform inference over such programs. So here we aim to solve this Bayesian inference problem over Bayesian purpose programs, and actually there are two classes of methods, such as process methods and also static analysis methods. So if we adopt the process methods, then we aim to derive an estimate of this posterior distribution in a lightweight fashion. And if we adopt this static analysis methods, then we aim to derive exact bounds for this posterior distribution. Okay. So here, to solve this posterior inference problem over Bayesian purpose programs, then there are several previous works, such as the first one, which is the most suitable one, which is through process methods. So we have that we can perform this approximate estimate via Markov chain Monte Carlo, and then we may also solve this problem via variational inference. But here we focus more on this guaranteed bounds, which adopts static analysis method. So there are several previous works, such as for bounding loops. We can unroll the loops to obtain the whole behavior of the loop, which has been implemented in various programming languages, and there are also several works to address this guaranteed bound problem via over unbounded loops, such as one can use this general function method to solve unbounded loops with discrete probability distribution, and we may also use this recursion unrolling and tries to abstract the continuous distribution via intervals, and also use widening to terminate this unterminating cases in unrolling. This is implemented in GBPI. So here we propose a polynomial solving method to handle Bayesian purpose programs with unbounded loops and also continuous distributions. So here is the outline of our approach. So we use fixed point theory and also optional stopping theorem, and we use constraint solving for polynomials, which has been done for a while. Our major novelty lies at the truncation operation, which is crucial to adapt polynomial solving methods to the posterior inference of Bayesian programs. And we evaluate our approach with this GBPI, which is the most rated tool. Yeah. Okay, so we'll first review some mathematics behind. So here, so here we use fixed point theory where we can derive a prefix points to serve as an upper bound for the posterior distribution, and a postfix point as a lower bound if we have if we guarantee that the program terminates officially, which ensures that we have a unique fixed point. And we also use optional theory, where it is one thing that we can use super martingales to derive upper bounds, and also some martingales to derive lower bounds. Okay, so these things are all done. And here I would also like to remark that so here we have a bit non-classical setting for our posterior inference problem, because here we introduce weights and we have weights which is multiplicative, which means that if we have a weight statement like score, say here this is score WT, and then we multiply this WT value to the current cumulative weight to obtain the new weight. So here weights are multiplicative, and also we define the posterior distribution from the weights above. So so our contribution is that we first apply formula solving, which is none, but we find that simply apply this formula solving the no service to solve this Bayesian inference problem. So we propose a novel truncation operation. So the intuition is that we somehow restrict the program behavior onto a bounded range of program values, and then we accompany this truncation with bounds outside of the truncation. So that if the bounds outside the truncation are correct, then we can get the correct bounds for our posterior distribution. So we also in our research we find that for several Bayesian inference problem, we have that somehow we need to deal with ways that gets multiplied again, so that there may be an integrability. So there may be an integrability issue inside the problem. So to handle this issue, we somehow propose a multiplicative variant of this OST, which is optional solving theory, and we find that this works to address this issue. So we'll see later. Okay, so so we illustrate our approach about this, I think, very standard example. So this example is that it models a random walk of the pedestrian. So you can see that from the first line of the code, we have that we assign the variable stat with a value which is uniformly chosen from 0 to 3. So if you are familiar with the Bayesian inference, then you know that this is a prior distribution, which reflects the prior belief of the initial parameters. And then we have working variables, which is post and state, which means that post records the current position of the pedestrian, and this records the current. It records the total distance traveled so far by the pedestrian. Then the behavior of the pedestrian is stochastic. It is specified by the loop below. So we have that until post is until post is smaller than 0, which means that until the pedestrian arrives at the origin, repeatedly have a movement where the movement is either forward or backward with probability both 1/2, and along the direction we have that the travel distance is also stochastic, which is uniformly sampled from 0 and 1. So this is one loop, and we know that this loop will terminate with probability 1 because it is a symmetric random walk, and at the end of the program, we have this score statement, which is the score of this normal 1.1, 0.1, which is the density function of the normal distribution with mean value 1.1 and variance 0.1. Yeah. So this score statement says that the pedestrian travel so far measured by odometer, it is 1.1, but with the normal error. Yeah, yeah. So we return this start variable to so the start variable is the initial parameter, which means that we wish to perform the posterior inference for this initial parameter. Yeah. Okay. So here some remarks on how to define this posterior distribution. So here we have the so here we first define this expected weight. So given a subset U of real numbers, so we simply define this expected weight restrict to this U as the expected weight when the return value is falls within U, and then we define this numeric constant, which is the unrestricted weight over the whole real line, and then we define this posterior distribution as the ratio against this numeric constant. Okay. Okay. So the problem now arises on how we analyze this posterior distribution. So we could apply polynomial solving, such as we can sketch the main steps here. That we have a polynomial template at the entry point of this while loop, which is here. It is h in blue. And then we can apply prefix point conditions to this h, whose details I do not wish to go into. It is sort of calculating the expected value of h after one loop iteration of h, and then we have that this expected value is smaller than or equal to h, and then we apply polynomial solving to this inequality. So these things are all known approaches, but we find that simply by applying this, we only get the constant bounds. So it seems that there is some problem inside, and we find that the problem is that for this working variable post and dist, we have that their values in this program they can be unbounded. So they can take any value, any non-negative real value. So somehow polynomials are not so effective on this unbounded region, as someone may recall that we have Variational's process theorem, which states that any continuous function can be approximated up to any error by a polynomial, but only over a bounded region. Yeah. So here, to make this polynomial solving effective, we need to have a truncation operation that first truncates the value of post and dist onto a truncated range. A bounded range, and then we have that, and then we try to solve, try to apply the polynomial solving over this boundary range. So So here we see that we first apply this truncation where we specify it to 0.5. I mean the square between 0 and 5. So that is the value of both post and dist. It is within 0 to 5, and then we somehow derive an upper bound outside the truncated range. So here you see that it is very small, which is 2.1 times 10 to minus 330. So this bound can be derived by examining by looking at the monotonicity of this program. So it can be easily derived, and then with this truncation range and also this upper bound, we then solve this this problem solving over only over this truncated range. So here we see that this truncated prefix point condition. Here see that the expected value of so here it is a summation which is b prime times h prime plus b prime times m, which so here this m it is it should be the second one should be the negation of b prime. Which means that it is outside the truncated range. So here the prime means that we have performed one loop iteration, and if it is outside the truncated range, then we simply have this upper bound m here, and if it is inside, still inside the truncated range, then we'll have this. Then we have this have this h prime here, which is still the one step expected value from h after one loop iteration. Yeah. So after this we have so this is the key step of truncation. So after this truncation, we can solve this Bayesian inference problem over this example. So okay, so yeah. So there are some assumptions for problem solving. For example, we need to have a polynomial approximation for the score function, because here you see that the score function is not polynomial. So we need to have certain polynomial approximation to this, and so because in the whole process we only allow polynomials. So here we need to have polynomial approximations whenever possible. Yeah. Okay. So so here in our research we find that there are some Bayesian inference problems which has a score of weight greater than 1 inside the nobody. So if we have unbounded loops here, then it may be the case that the score value may incur an integrability issue. So here we derive a new OST variant to handle this case. Yeah. Okay. So so this is our overview of our algorithm, and you can see our experimental results. So these are for the posterior inference. So you can see that. Since I do not have enough time, so I just quickly go through these results. You can see that the bounds of our approach are quite close, and we also have evaluation on assertion probability, and you can see that our bounds are also quite precise. Yeah. So thank you for your attention.
Thank you very much. If someone's got a quick question, I'm sure we can do one quick question. I think we've only got time for one though. So please state your name and affiliation before you question.
So I'm Peter from University, Czechia. Thanks for the talk. I have a question about this new variant of the OSD. So this condition that the change is kind of multiplicatively bounded, that's a absolute one-step change or expected in expectation?
It's still absolute, yeah.
And there are, like for these additional extensions by Wang et al. From the previous literature, they typically impose some additional conditions like exponentially decreasing tail bounds.
Yes,
Do you
yes.
also have something
yes,
like this
yes,
here?
Yes, yes. We use this to cancel out this multiplicative scaling of score values. Yeah.
Okay, thanks.
Right, thank you very much. Our next speaker is Guonan Wei from Purdue University. And Guonan is about to start a postdoc at Tufts, I believe.
As a professor.
As professor, yeah. Even better. Yeah, so Guonan's about to start at Tufts next year. So, and Guonan's going to talk about contracts for contracts, consolidating smart contracts with behavioral contracts. Thank you.
Yes, thank you, Steve. So good afternoon, everyone. My name is Guonan, and today I'm going to talk about work about contracts for contracts. It's a fancy title, but our paper is actually titled Consolidating Smart Contracts with Behavioral Contracts. And this is joint work with Danning, Wuqi, Yongwei, and Zhuo Zhang. So let's start with what is really smart contracts. So they're contracts in the sense that they specify some form of assumption and guarantees, but between business parties about some transactions, right? But smart contracts, they're also programs in the sense that they're autonomous programs signed and stored on a blockchain. And the blockchain mechanism will ensure that this agreement will be eventually realized among our business parties. In this sense, they are sort of smart programs, right? And there are a lot of different smart contract program languages and blockchain platforms. And one of the most popular one is called Solidity, and it's running on the Ethereum blockchain. And this pie chart shows the kind of basically the market share among different blockchain, and you can see the blue pie is the total value locked on the Ethereum blockchain. So it's basically really the majority blockchain, and Solidity is the program language to write smart contract programs running on Ethereum. And as a program language, the programs in Solidity will be compiled to a bytecode running on the Ethereum virtual machine and in a decentralized way, right? But just as all programs, they have bugs, but in the setting of smart contracts and blockchain, those bugs can be attacked and can be exploited and causing real money loss, right? And the table here, which is I get a screenshot from a study at ICSI last year, which is also authored by one of the co-authors of this paper. They just list several attacks, and you can see the total amount of fund loss is over, I think, $200 million US. That's really a lot of money. And one of the reasons that those programs can be attacked is because of the lack of clearly specified safety conditions. So programmers sometimes just omitted those conditions because of overlook somehow. But as PR researchers, we sometimes blame the language because the language does not provide enough mechanisms for programmers to specify and enforce those safety conditions. And interestingly, in the research community, there's also a notion called behavioral contracts. And this is a kind of metaphor, and it also specifies assumptions and guarantees between software components. And those behavioral contracts, they are sort of specifications. And those assumptions, you can think of they are preconditions, and guarantees are postconditions. And in a language with behavioral contract support, programmers can write down those assumptions or guarantees in the same program language as a host program language. So this is very convenient to use and easy to learn for programmers. And those conditions will be monitored at runtime if there's any violations. And this will further help with maintenance or debugging of the program. So the idea of our paper is to think about, there are two similar notions, they're both called sort of contracts, but for different entities. And what if we can apply apply the design by contract approach to smart contracts, right? And more precisely, in this work, we propose a console, which is both an extension to the Solidity language and also a transpiler that supports behavior contracts for this popular smart contract program language. And we can annotate rich precondition and postconditions to Solidity programs, and those conditions will be monitored for any violation at runtime. So this console as a transpiler to translate the program to implement this. And this will improve readability and maintainability, and potentially, because we have a more convenient way to specify those conditions, this potentially could further help with fuzzing or static verification, etc. Right? So let's look at example. Let's look at example how it looks like, right? So this is a function called getPrice, and it's kind of getting the price from an input value of this chain link, and it's calling a function over this chain link, get latest round data, and return this rate from the oracle with the ETH Ethereum price, and eventually the programmer can call this getPrice function, right? But the programmer also want to ensure that whatever the price is returned by this function is bounded by a flag duration, like this 95% or 1.05%, right? This is a post condition, and the programmer can just write down a little bit more annotation on top of the actual function to use this ensures keywords to write down the post condition. And this will be just checked at runtime when calling this function, right? So this is really all straightforward and simple to implement. This is not really much different from assertions. But now if we look at this function, there is an argument, which is an address argument called chain link. What if we want to say something about the argument chain link, right? And here the argument is an address. It's kind of like a little bit special data type in Solidity. And it's basically integer. It's like pointers or references in ordinary program languages, but it's 160-bit integers. And it's also first-class values. You can pass it around, storing into other data structures. That's all okay. But as addresses, they represent other instances of contracts or users so that you can interact with other contracts and users to make transactions or transfer monies, right? So they contain those callable functions. Like here, we're calling this latest round data on chain link, right? Because this chain link is an argument to get price, we may think about we can add a precondition to get price to say something about what chain link should behave, right? But this is not really an easy job to do, because when we are calling this getPrice function, even though we own this argument, but we do not know the potential argument when calling this address, right? We do not really know what's the actual argument potentially taken by the chain link and what's the return value of this ETH price when calling this getPrice, right? So we cannot really call this because this is kind of like a similar higher order essence here, right? So this is a unique feature supported by console to express and monitoring those conditions for addresses and their latent costs. And our idea is not really entirely new thing, because we borrow ideas from previous research in functional programming community, and this paper from Bob Finland and Matthias Felisen about contracts for higher order functions, because we found the problem is quite similar, but there are already quite good solutions in functional programming community. But of course, we need to tailor the solution to the setting of Solidity and smart contracts. And the basic idea in this paper is really to delay the check of those behaviors of higher order functions, especially when functions are used as values of other functions or return from other functions. Right. Before I'm going to talk about the actual mechanisms, we can revisit this function and look at the example here and how the actual specification looks like. Right. Here are two additional require statements. This is actually, we simplified from a real world smart contract programs. And there are two requirement statements to check the updated time and also the return price for certain security reason. And we don't really have to annotate those things here. We can just also write all the specification along in the single place using this where clause, and we can add a little bit of signature about the chain link and the latest round data, what the returns, what are those binding names we need to use, and we use the same syntax to ensure whatever the post condition already annotated here, right? So this is the post condition, and we can basically remove those two conditions from the function body. And the checks will be preserved whenever this chain link is passed around in the function body or when it's called multiple times. And all those checks will be preserved and actually performed, ensured by our compilation schema. Right. So this is really good for decoupling, especially repeated low-level checks from business logic. But now the problem is we need to know when to perform those checks of addresses class, because the trouble again here is those addresses, they're first-class values, and they can flow around, right? And the basic idea we did is we implement a whole program transformation of the annotated program, and we take the console as a transpiler. We take the annotated program and we compile it to the ordinary Solidity programs, which can be directly running on the EVM virtual machine. And there's a translation, a little bit formalization, more details in the paper, but I won't talk too much here. I just want to explain a little bit more about how we implement those things to track addresses. And the basic idea is first we want to change the value representation of addresses, because the row addresses, they're just 160 bits integers. And we want to encode additional information about what conditions should be checked when calling what functions on this address. And when the call actually happened, we decode those additional provenance information and decide what are those conditions should be checked actually. Right. So the example here roughly demonstrates the idea. We have originally a function f and it's taking an argument adder and then call adder the g function over adder. And then we translate to change the value representation, which is the type here. It's a guarded address. And then at the beginning of this function, we would attach the specification to this guarded address value representation so that later we can use those information. And the call side is also rewritten in the sense that we get a dispatch function taking both the guarded address and the normal argument. And inside of the dispatch function, we will decode the actual provenance information and perform actual check around this value. Right. But now there's a caveat actually. We must be actually careful because we're dealing Solidity and EVM. And there's a quite different cost model on EVM because all transactions on EVM, they take a transaction fee. And those transaction fee, they are related to how much storage you use in your program. If we are storing more information into those addresses values, we may cost additional transaction fees, which is undue for any users if they want to use this thing in a real business setting, right? So but luckily there's also a trick in the EVM platform. Even though the original address is 160 bits, but for loading and storing those values, less than 256 bits causes roughly the same amount of gases. So we can exploit these things to basically expand the addresses values to 256 bits and use the additional information to encode those specifications. Right. Here we can use additional 96 bits to encode the specification. And you can see here, we first expand the row addresses to from 160 bits to 256 bits, and then we can use that higher bits to mark which is precondition and postcondition to be checked. And at a later point at the call site, the dispatch function will read those information and get to know what are the actual checks here. And this actually causes very little overhead, which we will see later in the evaluation section here. So for evaluation, we build a prototype tool, and we want to know two questions basically. The first one is how expressiveness of console is. So especially in the setting to express those security differences. So, and we can also to see how much, to what degree we can decouple those security checks from business logic. And the second question we're interested in is how much overhead is introduced by our console translation. Right. And the first, to answer the first question, we collected around 20 cases from the real-world attack databases, and you can see roughly a summary of those attacks and the total loss of those existing attacks and the root cause of the vulnerability. They cover different varieties, vulnerabilities. Some of them are quite famous, like reentrancy, and some of them probably not, like integer overflow, which is also a common software mistakes here. So the total amount of loss, it's a crazy number, but they already happened here. And our evaluation is compared against those low-level assertion checks, because their attacks already happened, and people already patched those programs using just the assertions to specify those critical conditions. And we want to see whether we can use console to simplify the specification of those security checks, right? And the result is pretty good, and we can basically as effective as those low-level assertions, but we can also simplify the program, especially the main business logic, really a lot. And you can see the table on the right here shows the line number reduced from the function, and roughly around almost a half lines of code in those functions being attacked can be extracted to our console specifications. So you don't really need to intertwine those assertions with your main business logic, which improves readability a lot. And the second question is how much overhead is introduced by console translate programs. And for this question, we already have those benchmark programs from those real-world attacks, and because we can only run 16 real-world attacks, and we also collected 23 contract programs from previous paper by Lee from the PLDI'20. Those are smart contract programs, are pretty standard protocols in the EVM solidity setting. And our baseline, again, is to compare with low-level assertions already patched in those contracts, because those low-level assertions already exist. And if programmers migrate those low-level assertions into our console annotations, we want to know whether they will cause additional overhead. And so this table shows the result we did on those 16 real-world attacks. And you can see the numbers on the right here is the gas, additional gas introduced compared with low-level assertions. And on average, it's just less than around 0.2% of additional gas, which is really a marginal number and doesn't really affect any really business purpose. And for the second benchmarks, we evaluate on those ERC protocols. And again, the result is similar, and we also have around 0.29% of additional gases. So those gases are really good numbers and marginal. So to evaluate those things, we also replay those existing transactions on a simulated blockchain to simulate the real-world setting. Okay. So this is about evaluation. I just want to quickly summarize. We propose this console as an extension and a compiler to Solidity, and the main feature is really this behavioral contracts for smart contract. It is much more expressive compared with existing work on smart contracts programs, because we can specify and monitoring conditions for addresses values and their latent costs. And we also have a little bit clever encoding about those values and the spec encodings, which introduce only marginal gas overhead running on the Ethereum platform. So we have a prototype, and also our evaluation data is on GitHub. Thank you for your attention. I'm happy to take questions.
Anyone has a question?
So, very good talk. So if I understand it correctly, so your behavior contract is actually a dynamic check, right?
Right.
So as you said, if you have a bug in your smart contract, you will lose money, and if you have overhead in your dynamics check, and you have some transaction fee, so why don't you not choose some static check, for instance?
Yeah, that's a good question. There are already existing a lot of work on static analysis and static verification of smart contract programs, but not all information you have is available before running on the blockchain. And if you're doing dynamic analysis, you have more information to know what actually happens. And because we're following this behavioral contracts approach, the programmer can write arbitrary functions or computations as specifications. They're executable, but this can go beyond the capability of static analysis sometimes.
Yes, maybe fall to the old question. So who can verify this your behavior contracts?
Only the programmer, or ideally there some business person design this contracts from the business perspective. There are some people implement those things.
Yeah,
and those behavioral contracts should be more close to the actual business contract.
Okay.
I think that's probably the ideal case, but I'm not sure how much that's reflect the reality.
Yeah, okay, thank you.
Yeah. Thank you.
Thank you. Our next speaker is AJ Brahmakshatriya, who's at MIT with his co-authors, and he's going to be talking to us about staging layouts for high-performance custom host network stacks. And AJ will soon be on the market, so if you're looking around, please make sure you come up to AJ and have a chat with him later.
All right, thanks for the introduction, Steve. Hi everyone, my name is Ajay. I'll be presenting NetBlocks, which is, I'll be showing you how to stage layouts to create this high-performance network stack. This is joint work with my collaborators, Chris Reinhard, Professor Manya Gobadi, and my advisor, Professor Samana Marsinghe. Okay, so the motivation for this problem was very simple. A year ago, we were working on some high-performance network applications for data center settings, and we realized that there's a problem. When you start to write your applications, you basically have a choice of two protocols. There's UDP on one side, which is simple and fast, stateless, and has minimum overheads and works great. And on the other hand, you have TCP, which has in-order delivery, reliable delivery, maintains congestion control, does a lot of handshakes and stuff, but obviously comes with a lot of overhead. And if you happen to need something in the middle, where you say you need in-order delivery but not necessarily congestion control or something like that, you basically have to write things by your own. Like you have to spin up your own protocol from scratch. Why would you want something like this? The answer is also very simple. It's because of performance. Here I've shown a round-trip latency CDF for 10,000 requests for a echo application, basically. And these are the two extreme plots for UDP and TCP. As you can see, TCP is more expensive than UDP. But if you start adding other sort of protocols in the middle which implement individual sort of features like in-order delivery only, or checksumming only, or just some variations of the similar protocols, you can see that the performance is actually somewhere in the middle. But most importantly, it's actually quite far away from TCP. So if you start from UDP, but you only want in-order delivery, the only option you have is to go all the way to TCP, whereas you could be paying less based on what you're using. And this is what we essentially want to support. We want to carefully select features and pay only for what you're using. Okay, simple problem. The simple solution is you wanted to build this sort of a modular stack called NetBlocks core or network stack core, where you can essentially plug these features that you want, not just which features, but also what versions of them. Like you can implement reliability in different ways or congestion control in different ways and create your own stack. But not only that, we wanted to take this opportunity to also create a stack that's extensible, which means that the network engineers can also essentially implement their own small features that they can add onto the stack level itself to get more features than what is currently available. So in example, encryption. You could do encryption at the stack level so your application doesn't have to worry about it. And this happens all the time, by the way. Quick Protocol, which is implemented by Google, does have some sort of encryption support at the stack level. Okay, we started implementing this and quickly ran into a problem that many of you might have run into before, which is that writing high-performance code is really hard. When we start to write something like a modular stack like this, there's basically three approaches. The first is you write very hand-optimized implementations. We see this all the time. Like Quick is an example of something that is handwritten to be optimized. This implementation is obviously high performance. It's meant to be high performance. It is relatively easy to implement. Not for me, I'm not a network engineer, but for someone who has been writing network code for ages, they can write a good protocol in a few months, maybe. Yeah. But the problem with it is it's not general. Like you wrote an implementation and that's what it does. You can't change it. If you change it, it's gonna break or it's gonna not work as fast or whatever. The other option is you make a network library where you can sort of like chain together stacks and you can like layers can be attached together through some queues and you can make your own custom protocols. This thing is obviously general because you're choosing what you want at the network or the library level. It is also easy to implement, maybe easier than the hand-optimized implementation. However, unfortunately, you pay the price through performance. You have this cost of abstraction that comes from the modularity that slows your whole process down. And since we are compiler engineers, our favorite option is to write a DSL compiler or a compiler that can generate the stack for you. This has the added advantage of being high performance because you're generating specialized code for your specific implementation. It is also pretty general. You can generate a lot of protocols from a single compiler. However, it's not easy to implement. And what I mean by easy to implement here is if a network engineer comes around and wants to implement new features, they now have to learn how to write compilers, which we all know is pretty hard. At least I like to believe so. OK, so what we want is something in the middle, which is easy to implement, high performance, and general. By the way, this research is not sponsored by Google Chrome. This is just a coincidence. OK, so we set out to write this stack, and we tapped into our previous knowledge, which says that multi-stage programming or metaprogramming is a good solution for performant and general solutions. In this talk, I'll extend this to say that multi-stage programming is also easy to implement as long as it is done right. And the right way to do this, in my opinion, is to use our previous work, which is Build It. Build It is a type-based multi-stage programming framework embedded in C++. Before I go into how we're going to use this, I'm going to quickly explain what this means. So first, let's explain what multi-stage programming means in this context. A typical single-stage compilation workflow works like this. You write some source code, you compile it with your favorite compiler like GCC or Clang. You get an executable, you feed your input, and you get your output. That's single-stage compilation and execution. Build It generalizes this to multiple stages, where you have some source code, you compile it with your regular compiler like GCC or Clang, get an executable, feed in partial inputs. You provide parts of the inputs, and then you get as output more source code, which is specialized for those inputs. Compile it again with the compiler, get the executable, feed in rest of the inputs, and then get the final output. Again, this can be generalized to multiple layers, but multiple levels, but we'll be doing two-stage in this particular example. The thing I want to point out about this is Build It is purely a library approach. So all these compilers and toolchains that we are using along the way are standard compilers. There's no compiler sort of magic here, so it's very lightweight in that sense. And the second point I want to highlight is this is a very explicit form of multi-stage programming, which means that the output code that's specialized is produced as C code instead of some intermediate inside the compiler when you're using, like, say, C++ templates or something. OK, so with that in mind, let's just quickly go ahead and see how Build It works. Build It essentially introduces two new type templates, dynamic of var and static of var. Everything you write with dynamic of var is produced as it is. And everything you write with static of var is completely validated in the first stage. So here's an example. I have the power function, which has two inputs, base and exponent. I've marked the base to be dynamic of integer, and exponent is static of integer. And since exponent is static, all the control flow, all the conditions based on that is completely evaluated to give us an unrolled code. And if I make a small change, if I make the base static and I make the exponent dynamic, you get something like that, where the control flow and the expressions based on the exponent are retained, whereas the base just becomes a constant in that code. OK, very simple programming model, two new type templates, wrap them around whatever you want, and you can get partial evaluation. So the way Build It internally works is it's a lot of magic in the sense like there's a lot of operator overloading that essentially extracts all the expressions that you write for dynamic variables. And for statements and control flow, we have this system where we repeatedly execute your code to explore all the branches and then combine those branches to give you basically a single code. There's a lot more details about this work in our previous paper, so feel free to look at it or come talk to me afterwards. But OK, that is a primitive that we have now to start building a network DSL. Let's get back to node blocks. What are the main challenges when you're writing a network sort of stack like this? The first problem is that these features that we're implementing change behavior globally. What I mean by that is, say I decide to enable a feature like reliability. And once I enable that, and the logic that sends the packet now needs to start attaching sequence numbers to it. The logic that receives the packet needs to checking if those acknowledgements have been received or send acknowledgements and so on. If there's a timeout happening somewhere, then you need to retransmit, duplicate acts and so on. You need to do handshakes and goodbyes and stuff like that. So which means a single feature can change a code in a lot of places. It's not like localized in one place. And the other big problem is that features affect state and structures globally. What this means is, again, in the case of reliability, once I enable it, I need to start putting sequence numbers into the packets. I need to keep a redelivery buffer for each connection that I have open. And I also need to change some global state to have like timers and stuff around. So a small feature can change the whole picture globally. So what we want is modularity, but that modularity obviously comes at the cost of performance or features. This is a problem. So what we noticed, however, in this case is that this modularity and all this configuration happens at the time of choosing the features. there is no runtime modularity. Like once you have decided your features and once you have decided the flavors of your features, everything is fixed. So in the staging system, if we can do all this modularity in the first stage and generate specialized code for your stack, some of these overheads can be eliminated. That's basically what we did. We implemented a high-performance aspect-oriented programming system. Aspect-oriented programming system, if you know. Yeah. So what we have essentially here is a NetBlocks framework. At the top is the application. At the bottom is the physical layer, which is basically handling all the physical communication between the nodes. And then in between, we have the framework. The framework has in between these so-called paths, like the send path, the established path, ingress path, and so on, which correspond to roughly to the control paths that can be taken in the stack at runtime. And on the left, we have these modules, which implement these individual features. Now, what these modules can do is they can insert hooks into these paths to sort of change the behavior of that path. They can insert logic in any of these paths in a very modular, dynamic way. But we want to get rid of the overhead for that. So let's start with a simple implementation of aspect-oriented programming system. At the top, I have defined the module class, which is a generic sort of interface for all modules, and it has the virtual functions for all the hooks. Now, a module like reliability can sort of inherit from that and add hooks to, sorry, there should be an inheritance there, which I missed, apologies, which inherits from the module class and then implements those hooks as functions, which finally, there's a code that iterates through all the registered modules and invokes their hooks one by one and dispatches the calls. Now, what we do is, with a very small change, we basically first make all the parameters like the packets and the connection data structures as dynamic, so they will be generated. However, the module itself, like the modules here, themselves are static, which means that the registration of the modules, the configuration of the modules, the iteration to the modules, the virtual dispatchers all happens in the first stage to give you very clean, inlined, optimized pack code that has the logic specifically for your feature. Not just choosing of modules. Now, within your modules, you can have if conditions based on like configuration parameters, which will generate different logic based on what features and what flavors are enabled. So that solves somewhat of a problem of sort of specializing for features. And with that, we implemented these 8 modules, which implement different features and their versions. On the right-hand side, I just don't need to get into all of this, but on the right-hand side, I just have like different options you have for these modules. And at the bottom, you can see that we can generate up to 864 different combinations from the same stack by just choosing different versions of the module. And this is even without specializing the stack for more optimizations like, which I'll talk about later about like data layout optimizations. So just by choosing features, we get these many flavors. OK, so let's go to the next problem, which is about data layout changes because of features. So there are 2 types of sort of changes that can happen, or 2 types of events that can change the packet layout. The first is based on features. Like if you choose a particular feature, it might want to add headers or fields to your packets. Like if you enable congestion control, you need some congestion headers in your packet. And the second is based on deployment. What I mean by deployment here is the same protocol deployed in different scenarios might have different packet layouts. For example, one of the common fields that's there in all network protocols is the IP header. If you all have heard about this before, it's a 32-bit header which identifies where the packet is going, a host for the packet. But suppose you're deploying it in a scenario where you only have 16 nodes. Why do you want to play 32 bits for it? You can pack that whole thing into 4 bits and generate a very packed protocol. But at the same time, if you move to a different scenario, you need to recompile and generate a new protocol. What I'm saying is, as the deployment changes, the packet layout changes. We want a way to somehow programmatically change these layouts so that we don't have to manually go and change structures every time we are changing the protocol. We want somewhat like a staging of layouts, basically, like staging of code. So before I talk about my solution, let's just look at how it's currently implemented. Currently, if you look up at any network stack implementation, a library, or a handwritten implementation, that's typically struct like these, which are packed struct, so they are all the fields are all next to each other, which sort of implement the layer. And then you take the pointer to the packet, cast it to one of these structs pointer, and then manipulate the fields. You can read or write them. That's the typical way of doing this. Obviously, this is not programmable. You cannot like remove fields at first stage. But one thing we noticed while looking at these implementations is that structs by themselves are not objects. They're not data. They are just a way of describing to the compiler how to access those particular fields. So we can make that explicit. We can convert this process of describing to the to the compiler how to access those fields as code, and then we already know how to stage code. So then we can stage those layouts. That's the simple idea that we came up with. So how it works is we require the user to describe each packet sort of header to us in this simple sort of structure where they have to give us two pieces of information. One is the size of a particular field, and the second is the alignment requirement of that field. With those two pieces of information, then we can compute the offset for each field by first taking recursively the offset of the previous field, then adding the size of the previous field and aligning it to the alignment requirement of this field, which is done here. And once we have the size and offset of each field, we can basically implement functions like getInteger or setInteger, which will compute the address of the field in the packet and then dereference it to give you the value. Obviously, all the computation of the address and stuff, this stuff happens in the first stage. So what you essentially get is a very tight code that just has the exact code to access those fields. And the way you use it is you create a packet structure, you add your fields to it, and then you can directly access your fields by calling them by name and setting those values. And that generates basically code on the right. This is great. We have sort of like described the problem as code, staged it, and we got some modularity out of it. But now what we can start doing is we can also further optimize it. We can say, OK, I know this field is going to have a specific range. So take this range as a value, and then compute the number of bits required for it. And in the getInteger implementation, now we can basically generate precise masking logic to get and set those fields. The good thing about this is the way you use these fields will exactly be the same. Nothing will change in the module implementation. The only thing that will change is how the fields are defined. And then the generated code will automatically have masks and shifts generated to do the actual bit manipulation. So this is great. We can now generate very precise layouts for our packets. One thing that NetBlocks automatically does for you is also, if you choose, it can rearrange the packets in such a way that the alignment requirements are satisfied while minimizing the number of bits required to have the whole packet implemented. So with this, what we have done is, here's a sort of a layout for a typical Ethernet, IP, UDP, and payload stack. We first identified some fields that are redundant, so things like length, which are implemented as part of IP and UDP both, or things like checksumming, which are again redundant, or things like in red, which are basically not useful in many scenarios, so we just drop them. And by removing all those, we get a packed layout like that. Furthermore, we did like the deployment optimizations where we said, OK, I know my hosts are only going to be 16 or in 4 bits range, so can you shrink them down and so on. And we get this very shrunk protocol that does almost UDP-like things for just a 2-byte headers, which is great for a scenario where you are throughput bound in ways. So one side benefit of this is because the compiler has all the information about your packet layout, it can just automatically generate packet inspectors for you that you can insert in Wireshark and just debug your custom ad hoc protocols that you're creating. So with this, comes the third part, which is about extending, which I promised would be very easy. And I don't have any slides for it. The easiest way I'm going to demonstrate that is by just implementing a new module right in front of you. So I have, So I have here the NetBlocks implementation that I have created. I'm going to quickly implement an encryption module, a dummy encryption module, and let's see how much effort it takes. So the first thing I would do is to implement a module header for a module class for it. So I've already implemented an encryption module here. All it has that's special is these two hooks, send hook and ingress hook. And then what I'm going to do is implement this module actually. So let's go here. Oops, sorry, it's already open. OK, so here I've already implemented like the bare bones hook here. All I need to do is like go to this packet and encrypt each byte. So what I'm going to do is for builder and I equals 0, I is less than payload len I plus plus, and then I'm going to say payload of I equals, I'm going to do a very super secure route 32 implementation. So that gets plus 13 modulo 256, right? That's it. This is my implementation of the encryption module. And then for the decryption side, I'm going to take the same thing on the ingress side, put this here, and just this becomes 256 minus 13, right? This should decrypt it. Okay. Oops. And then finally, I'm just going to go to my implementation. It's a simple implementation. And then I'm going to insert my module. Let's insert it before checksumming. So checksumming is done with the encryption. So I can say encryption module instance dot init module. And this is a simple module, doesn't need any new fields or whatever, but they can also be added. OK, let's just compile this and look at how a stack looks like. Modified a header, so it's compiling everything, but it should not be too long. And then I'm just going to quickly compile a test case. It's generating a new protocol. So let's just look at the generated protocol. Let's look at the send function. And we can see towards the exit side, we have a crude loop that's iterating through each value and is doing our route 32 encryption. And on the ingress path, when it comes in, the packet comes in, it basically again iterates through those packets. Oops, sorry. Iterates through those packets and does the decryption, which is should be here. Yeah, there we go. It's doing some decryption here. Again, these things can be optimized further if we need to. So that's just the simple demonstration that extending NetBlocks is also as easy as just picking features and writing your new library implementations. OK, but then let's get to the evaluation quickly. So we evaluated our performance of our stack on a real Nginx unmodified server. No lines of change to the Nginx server. I'm just going to zoom in onto this new protocols. The same result as before. You can see that as you pick and choose features, the performance gets a gradient. And you don't have to go all the way to TCP to get the full features. You can pay less features. We did a similar evaluation for throughput, where you can see that the throughput drops a lot when you have reliability enabled. So you don't have to pay that whole cost when going from UDP to something that's smaller. And finally, I just want to quickly talk about where build rate is going. So build rate is currently expanding in all directions. We are adding a lot more DSLs on top of it. Breeze is a regular expression DSL. Shim is a compression DSL, and obviously NetBlocks. It's also expanding downwards. We currently support generating code for CPUs and GPUs. We're adding support for FPGAs. And it's also expanding sidewards in that we're adding a lot of toolchain support to debug your code better or automatically migrate your existing code bases into build it without any lines of code change. I like to call this the Quasar of build it because of the way it's expanding. And finally, that's our website. If you have any contributions or if you have any questions, please reach out to us. Always welcome. Thank you.
We have time for one or two very quick questions.
Yeah, so this is an interesting talk because basically what you're doing, if I understand it, is you're taking ideas that were originally pioneered in the context of programming languages like AOP, stage compilation, even all of this stuff where we're doing data structure layout, and you're making it, in some sense, available at the source code level to anybody who doesn't have to get in the compiler to do it.
Yep.
I'm curious how much expertise you think it takes to use these things that way, and how much else is going to start migrating out of the PL.
Right, so the expertise-wise, I think the majority of the expertise that we need is a domain experts. The domain knowledge is all you need because if you can write a library for your domain, you can write a compiler for your domain. That's the sort of big agenda we are trying to push. And I mean, we have had my master students working with me who have implemented entire modules into this, like compression, encryption, and so on. And yeah, I mean, they picked up the system pretty quickly. If that answers your question, I don't know. Okay, we can talk later.
Really cool work. Your idea of sort of defining these views of the underlying packet data through this code that you then eliminate through staging makes one wonder, is there a reason to update the views? Do you ever have to modify the packet through these programs you're writing?
Yeah, so we have set integer and get integer kind of functions, so they can manipulate those data using those views. Are you asking about changing the views themselves?
We can talk offline. I was just curious if you thought about other abstractions for defining those sort of getters and setters that.
I would be interested in like talking about that. Yeah, cool. If you can extend it further. All right. Thank you so much.
Okay, our final talk today in today's session is from Mark Moeller from Cornell, and he's going to talk about catch, the fast symbolic verifier for netcat.
Okay, thank you, Steve. So in networking, a policy in place at each switch is what determines what to do with a packet when it comes in. In particular, based on the fields in the packet, we could filter the packet, which is to say drop it, or update one of the fields, and ultimately make the decision of where to forward the packet onto the next host. And if we zoom out and view the policy across the entire network as just a program that takes packets as input, then it produces traces of packets as the output. So we could ask some verification questions about this program. In particular, for a given policy, can host 1 reach host 3, say, or can all the hosts reach all the other hosts? Let's say I have a client that I want to give a slice of the network to, and I want to make sure that the different client slices remain isolated, that is to say they can't interfere with each other. I might want to verify that as well. So we can answer a number of these questions with a number of techniques, but we're going to focus on reachability for now. And one appealing way to answer these questions is netcat, which appeared in POPL 10 years ago. And here's the language. It's pretty small. If you're not familiar with cleaning algebras with tests, that's the underlying theory that netcat is based on. It's mostly just regular expressions with some additional features to reason about networking. So in this case, these tests here are how you would filter packets, as I said, and then the assignment there would be how you modify packets. It's also how we model the forwarding behavior. I'm not going to talk about dupe, which is just about how we keep track of the traces that we're building up as we go. That's elided from the rest of the talk. But as you can see, basically everything else is regular expressions. OK, so the great thing about netcat is it's sound, complete, and decidable. That is to say, we have axiomatic theory, and that's the basis for the verification ultimately. To do an actual verification of a networking query, we convert both the program and the specification to automata, and then the verification itself amounts to computing equivalence of those two automata. Okay, unfortunately, in the past it hasn't worked all that well in terms of the speed compared to other techniques. So before we started this work, the currently available version of this netcat decision procedure was a tool called Frenetic. That's the blue dots here. And the state of the art in network verification is much, much faster. So here's a tool called APKeep. It's based on a line of work called atomic predicates. And just to orient you, because it's a log-log plot, the highlighted line there is 1 second. And then the frenetic implementation is timing out at around 5 minutes for many of the examples. These are all of the topologies in the Internet Topology Zoo, which is a database of topologies, and we've overlaid routing policies on top of them, and we're doing reachability of every pair of nodes in each of these queries. By the way, the size of that's the size of the policy. The furthest one out there on the right is called Kentucky Data Link. It happens to have 754 nodes. Okay, so that was the problem we wanted to tackle, is that the performance of netcat was limited in practice, and we've introduced some improvements here to speed things up significantly, but also make the verification queries more expressive. So first and foremost, we brought symbolic packets and the associated techniques to make this much faster. We've extended the netcat language to make the verification queries themselves more expressive and unlock additional performance. And then actually we're able to give symbolic counterexamples as a result. Okay, and indeed, we were able to catch up to the APKeep here. So the green diamonds here are where we're headed, and then I'll explain the orange diamonds as well. But just to take a step back, I want to explain why netcat was hard to decide to do decisions in the first place. And I want to run through an example here, but these are two netcat automata, so it's not quite as easy as determining the equivalence of finite automata. What they look like is these double arrows coming out of them are essentially the analog of accept or reject states. But in addition to the state space, I also have to grapple with the packet space of all the packets that can appear in the network. So what I'm looking at down here at the bottom are essentially predicates that are also allowed to filter and modify packets. And the transition is allowed to filter and modify packets as well. So to run through an example, if I start with a packet with just 2 fields and 2 values, the automaton on the left always drops this packet. Okay, and I just need to verify that that same behavior happens to the automaton on the right. So start with a packet, and then I have to sort of move across this transition, and the plus is a non-deterministic choice there. So because I passed the filter on the left, I can just copy the packet and now consider the same packet on this other state. The dot is a conjunction, and so in this case, because f is 0, then I don't pass the filter that checks as f is not 0, and I end up dropping the packet that way. But again, this was only one side of the non-deterministic choice, so I could optionally also just assign g to 1 and consider the packet that results over there. But in that case, I'm dropped because I checked that g is not 1. OK, great. I've still only verified that one packet has the same behavior on both automata. So I have to start over again with a new packet where f is 1 and g is 0 now. Again, that's always dropped. On the right-hand side, I don't pass the filter on the left this time, so I have to set g to 1. And the resulting packet there, again, is dropped for the same reason. OK, and now I'm iterating through the whole packet space. And the important point to note here is not for the, of course, two-field, two-value example, but the packet space can get large with the bit width of the header, right? That's exponential. OK, so there's the performance again, and I'm being slightly unfair to Frenetic because what Frenetic's doing is a little bit better than what I showed you, but that's the right intuition for why it's so much slower. OK, so we introduced symbolic techniques to speed this whole process up, and I want to go back to the example and start to blend in the techniques that we're going to use to make this faster. OK, so first and foremost, binary decision diagrams are a popular and sort of hero of these types of analyses. And the idea is I'm going to represent a whole set of packets. In this case, off to the left, I have the set of packets for which f is 0. That can just be represented by this BDD that basically is a decision tree. So you ask, is f 0? If so, then yes, you got to the true block. That means you're in the set. If it wasn't, then you weren't. OK, so to redo the analysis we just did on this automaton, we start with a symbolic representation of all the packets and push through this transition, computing the BDD that is all of the packets that could result from starting from anywhere in the universe of packets and getting through this transition. And actually, if you look at it, it makes sense, right? If f is equal to 0, then I'm definitely in the set, right? Because I could have passed the filter on the left. And otherwise, if f wasn't 0, then we know g has to be 1. Okay, and so that's the correct set of packets that could have passed that transition. But then it's easy to check that none of those would pass the guard at the bottom. Okay, so I've just redone all the work that we did before with by iterating the packet space, now with one pass through using symbolic packets. Now through all of this, the thing that I hand waved just now was how am I representing these transitions to make those symbolic updates to those packets. And this really becomes the crux of the issue for us. And this was deciding the representation for this and doing this computation was really the trickiest part of this work. Okay, so again, I'm going to take inspiration from BDDs, but it needs to be more complicated because now I'm representing sort of a whole relation on packets, that is the whole space of updates that are expressible within Netcat. Okay, so I'm representing this transition shown with a symbolic packet program. I call it an SPP. And here there are going to be two cases based on whether f is equal to 0 or not. So the first part looks just like the BDD for a symbolic packet. But then the point is I have a assignment layer. And just because I tested against 0, I'm going to maintain 0 in that case. And well, because in the other case, there's no assignments to f. I'm just going to maintain for right now. And we'll see where we're going with this, because there are going to be two cases. Now, when I get to the layer for the field G, there are no tests against G anywhere in the transition. So those are both going to be the default case for now. But then the interesting thing happens when I get to the assignment case. And in particular, for packets for which f is 0, I have that choice of whether to pass the guard on the left or perform the assignment G equals 1. And that's why both of those end up in the true case there. But if f wasn't 0, you go back to the beginning and you follow your way down. If f wasn't 0, we know we're not going to pass the guard on the left, and so we have to assign g to 1. That's reflected in the legs down there. Okay, and the real punchline of SPPs was that we were able to come up with a way not only to represent the transitions like this, but actually that they're canonical. And by that I mean, even though there may be many ways that the transition could appear in the source netcat program, they ultimately are guaranteed if they have if a transition is semantically the same as another one, then it has the same SPP representation. And this ends up being a huge performance win for us in the implementation because we can hash cons and recognize the equality of anything once it's been canonicalized. Okay, then taking a step further out in terms of how the implementation works here. This slide is just giving you 2 examples of SPPs, P and Q. And then we can perform all the cleaning algebra operations on them as sort of algebraic operation. So what's shown on the right there is P symmetric difference Q, and then take the Kleene star for the 2 SPPs shown first and second. And this is just to tell you that we defined all these operations for plus, dot, and star. Those are the classic Kleene algebra operations. But then we also have intersection, set difference, and symmetric difference. Okay, taking one further step back, we would build from the original netcat program and the specification an automaton that looks like this, where the transitions and actually the output functions are all labeled by underlying SPPs. And as a result, the construction of these automata themselves are based on those underlying SPP operations. So that was kind of the core of everything. And we get this result that the automata are also closed under plus, dot, and star. And again, the set difference, intersection, and symmetric difference. And as a result, the key to answering the equivalence queries that were the original verification goals, if I have an equivalence query P equals Q, I can answer that by computing the automaton for P symmetric difference Q and just testing if it's empty or not. If it is empty, then they were equal, and the query has been verified. Now this only gets us actually to here. So everything I've told you, if you do all that, you've made a significant improvement on frenetic in terms of netcat, but you're not quite to the state of the art. That was when we introduced additional netcat features to unlock some of the additional power of the symbolic representation. Okay, so just to tell you in the frenetic way, or in the sort of naive encoding of all pairs equivalence queries, you write an expression that looks like this, and this is the equivalence query itself, but note that it has to happen for every I and j in the network, where n is the number of hosts that you're trying to verify the reachability of. Well, that's n-squared queries. On the other hand, if you know that the underlying representation are symbolic packets, what you're going to be able to do is only iterate over the hosts once and compute, leaving from host I, what's the symbolic representation of all of the reachable nodes, after considering all behaviors of the network, and check, is that the symbolic packet that represents all of the other hosts? And what I've done is reduce it down to only linearly many queries. And indeed, by doing that, the catch reveals itself as competitive with the state of the art there. Okay, and the last thing I wanted to mention was that sort of as an immediate consequence of this formula that I gave you before, because I'm taking the symmetric difference of P and Q and comparing it to empty, if it's not empty, then the result that I've computed is an automaton with these SPPs as transitions, and that thing is a symbolic representation of all of the counterexamples to the difference between the program you wrote and the specification. And so you could use that symbolic automaton to produce concretely all of the traces that witness the difference in behavior between the program you wanted and the program you have. Okay? And with that, I'm happy to answer any questions.
Do you have any questions?
So this is really cool work, and I love that it also works on equational fragments, which sort of motivates me to ask for expressive power questions. Like, could I do something like ask, if I added this new route to this existing network, would I get the same thing as this other network? That sort of stuff.
I think so, if I understand your question correctly, that you could do all that within the expressivity of our language, and then the equivalence query that you asked is just another equivalence to run against the solver. I'm not sure if I understood.
Yeah, that was about what I was asking. And can you also do inequivalence? Can I say whether this network is contained within the other one?
Containment, yes, because of the fact that subsets in cat is just, A is equal to A plus B. That because every inequality in cat is actually just also an equality, you can run that as your verification. And yes, you can do disequality, I guess, just to be clear as well. Yeah.
Cool.
Yep.
Very nice talk. So I noticed that your previous two slides is that you talk about if you have a loop to check the equality of them, so you can save the computation using your new extend the syntax, new extend the semantics. So I'm curious about, can you do one more step? For example, here is a loop, right? So you can try the symbolic version of the loop. Maybe that is the universal quantified I. Can you do it? Or do you think that is possible?
I see. You're saying instead of starting at a single switch, start with a symbolic packet that represents any starting point.
Yeah.
So we can phrase it this way, but well, I'm concerned the meaning is different because now you're just checking that each host is reachable from some starting point, and to get the universal quantifier the way you wanted there, I don't think that works. I think you have to do this, but I might have to think about it a little more offline.
Yeah. Okay. Cool.
Yeah.
All right. Thank you, Mark. Great talk. Let's thank all the speakers in this session, and there's time for a break now.
So welcome everyone to the session on security and cryptography. We have 4 very interesting talks today. And the first one is going to be given by Alexander from MIT.
Am I good to go? Okay. Hello, my name is Alexander, and today I have the pleasure of presenting. I have the pleasure of presenting our paper, a tester compiler with automatic data packing for simple and efficient, fully homomorphic encryption. This is joint work with Nicholas Samardzic, Simon Langowski, and professors Srini Devadas and Daniel Sanchez. Fully homomorphic encryption, FHE for short, is a type of encryption which lets us compute unencrypted data. This has the promising use case of enabling fully private computations in the cloud. Let's say we have a client who wants to offload the evaluation of some function to a potentially interested server. With FHE, they just send their data encrypted to the server. The server runs the equivalent FHE computation on the encrypted data, producing the encryption result, sending it to the client. As the server never decrypts any of the client's data, that data is kept fully private. While this sounds enticing, there are 2 potential obstacles to FHE adoption. The first one is performance. FHE is orders of magnitude slower than unencrypted computation when executed in a CPU. Fortunately, recent work in acceleration on GPUs, FPGAs, and especially on ASICs more or less bridges this gap. This leaves us with the second obstacle, programmability. FHE is different from just running your existing applications with the data encrypted. FHE requires using its own programming model, which is challenging to use. And just to give you a sense of that, there have been multiple papers published, each just porting one existing application to FHE. Taking a step back, we have programmers used to high-level programming languages, and we have this obtuse, hard-to-use interface we have to follow in order to compute unencrypted data. We want a compiler to solve this problem. And our recent compiler, Felipe, does so. With Felipe, the amount of effort necessary to implement FHE applications is drastically reduced without sacrificing performance. In fact, Felipe is the first FHE compiler to match the performance of magnitude FHE applications. Of course, we're not the first to think of making a FHE compiler. However, there are 2 crucial aspects of FHE programming in which Felipe makes major contributions, differentiating it from prior work. These are data layouts and noise management. Now, I'll give you an overview of both of them here, but the focus of this talk will be on layouts. I won't be talking much about noise management beyond the slide. If you want more details, see our paper. Layouts come into play because data is encrypted into large vectors, and once these vectors are encrypted, it's practically impossible to reorder elements. Minor applications avoid reordering elements by using many layouts. This produces efficient programs, but it's challenging to write manually. And prior compilers, well, they don't have a systematic way of reasoning about layouts. As a result, they either use only a small range of layouts, producing inefficient programs, or we have super optimizers. They explore everything, but they fail to scale beyond tiny kernels. With Felipe, one of our crucial contributions is a novel way of representing layouts for FHE. This lets us explore a wide range of layouts systematically and efficiently, producing efficient implementations of large FHE applications, drastically outperforming prior compilers. Noise is introduced during encryption for security and has to be managed using 2 auxiliary operations called rescaling and bootstrapping. Rescaling, prior work has found good ways to do automatically. Bootstrapping, not so much, because it shows up only in very large applications. With Felipe, we also contribute a novel algorithm for deciding when to bootstrap, which is the first such algorithm to match the performance of manual bootstrap placement. Now, before going to details of our contributions, I'm going to spend a few moments showing you how FHE works, and then showing you how the challenges of layouts show up. What I'm going to say here is going to be quite general, though some of it will be specific to Succinct ES. This is the state-of-the-art FHE scheme or FHE system, and for that reason, the scheme which Felipe targets. Data is encrypted into large vectors of fixed point numbers, and these vectors support only 3 operations: element-wise addition, element-wise multiplication, and cyclic rotation by a fixed constant. That's all. Since data is kept encrypted, we do not have access to individual elements. We cannot just permute vector elements for free. This is one of the crucial differences between FHE programming and more traditional vector processors or SIMD or GPUs. And further, for security, these vectors turns out they have to be quite large, on the order of 32,000 elements. Applications which don't have sufficient data parallelism to fill them, they still have to pay the full computation costs, effectively wasting the unused slots. Despite these somewhat limitations, FHE is still a great fit for applications in linear algebra and machine learning which have sufficient data parallelism. To see the challenge of layouts, we'll be working through an example consisting of a sequence of matrix vector multiplies. This is representative of applications like neural networks with fully connected layers, or recurrent neural networks. I'll be assuming that the matrix is moderately large, 128 by 128, which in particular means it will fill a 16,000 element ciphertext. Of course, I cannot draw 16,000 elements on my slides, so just for visualization purposes, I'll scale things down so the matrix is 4 by 4 and the ciphertext 16 elements. Now that we have our tensors, we have to represent them as ciphertexts. It's worth emphasizing that this choice of layouts is made by the programmers or the compiler, and it's not dictated by FHE. In this example, starting with a simple choice of putting the vector elements contiguously and the matrix in row major will turn out OK. Now we have our ciphertexts. What should we do? We can try multiplying them. This gives us some useful partial products. But like on second thought, it's very inefficient. This is utilizing less than 1% of the available slots, because we're just doing only one row of the matrix. To use FHE efficiently, we have to use replication. By rotating the vector and then adding it back to itself, we can double the number of copies we have. Doing that log n times, we have n copies. Now, if we start a procedure with replication and then multiply by the matrix, we're able to compute all partial products in one go. Pretty cool. And it turns out, using a similar sequence of log n rotates and adds, we can sum up all the partial products which correspond to each output element. This is efficient. If we take a moment, we were able to compute n dot product using only log n operations. There's a catch though. See our output? It's under a different layout than input. Now there are gaps between the elements. We cannot just take this procedure and apply it again on the output to the second matrix we have to multiply. What should we do? Well, one thought, let's try converting back to the original layout. By multiplying the vector with a specific mask, we can isolate each vector element in its own ciphertext. We can then rotate them individually, align them, and add them. This requires all of n operations, completely defeating the point of our nice replication algorithm, though. We don't want to do that. Instead, we should try working with the layout as is. We can still do replication, turns out, efficiently. The only difference is that we now get our data under a different layout. If you see here, for example, the copies of x0 are now all contiguous, where previously they were evenly spread apart. But never worry. So long as we also change the layout of the matrix, now to use column major instead of row major, we can still compute all partial products in one go. And again, we can sum up the partial products to our vector efficiently in log n steps. This shows us that this application can be implemented very efficiently in FHE, but it's also hard to do manually. Stitching these layouts manually is tedious and error-prone. And to make matters worse, if we had matrices of different shapes, well, we wouldn't just have these two layouts to alternate between. Each matrix vector multiply would require its own implementation. I want a compiler, after all, to do this. This is where Felipe comes in. With Felipe, we provide a Python-embedded domain-specific language, which exposes a data type representing an encrypted tensor. We use tensors exclusively because that's a natural way of ensuring we have sufficient data parallelism to use FHE efficiently. These tensors, they support a couple of operations. First, we have add, multiply, and rotate. These are the equivalents of FHE primitives. Then we have two new operations, replicate and sum. These are the analogs of the log n sequences we saw earlier. These are very useful for linear algebra kernels. And lastly, we have a couple of operations which by themselves aren't terribly interesting, but are necessary for completeness. But this is all. Using this small set of relatively simple operations, we can implement interesting algorithms efficiently. For example, matrix vector multiply, that's just replicating the vector, element-wise multiply, and then summing. Or, for example, this is an approximation of tan h using adds and multiplies implementing a polynomial. These are the kind of functions which we have to approximate in FHE because they're not supported natively. Now, if you're seeing this for the first time, maybe this looks somewhat daunting. How will I come up with this? It's worth remembering that these functions need to be implemented only once and then can be reused. Regular programmers don't need to worry about their implementation details. And this crucially is enabled by the fact that Felipe abstracts layouts and composition. This is why we can use this same code snippet to implement matrix vector multiply for both a row major, column major layout, and many more combinations. Felipe compilation proceeds as follows. We first execute our Python DSL to produce our IR. This is a tensor data flow graph. We then annotate each tensor in that graph with a layout. We introduce noise management operations. And then we translate our IR to a graph of FHE primitives. These are operations which can be executed directly on encrypted data. We support two execution platforms, a CPU and state-of-the-art accelerator Cryptographic. Now let's finally get to how Felipe represents layouts and how these layouts are assigned to tensors. We saw that given a matrix, we need to be able to represent it in at least two ways, row major and column major. these are different layouts. By layouts, I mean different ways of mapping a tuple of tensor indices to a slot index. This idea of different dimension orders, Felipe takes it and generalizes it. A Felipe layout can be an arbitrary permutation of dimension index bits. What do I mean? Given our tensor element, in row major, we get our slot index by first putting the bits of the I dimension and then the j dimension. In column major, it's similar except we use a different permutation. It's first the j bits and then the I bits. We also saw that we need to support ciphertext where some of the elements are not used for useful data, or we have gaps. To support that, Felipe lets us interleave arbitrary gap bits in our layout permutation. So in the first case, if we put the gap bits in the more significant bit positions, we get the first layout where our vector elements are contiguous, and then we have a large gap afterwards. Conversely, if we put the gap bits in the less significant bit positions, we get the second layout where we have a stride of 4 because we have 2 gap bits. This is a powerful representation which brings many benefits. The most immediate one of them is that there are now several operations which can be implemented efficiently by just manipulating metadata without any work in FHE. Transposing a matrix, well, that just requires reordering the bits in the layouts. Shrinking a dimension, let's say by a factor of 2, that just discards one of the layout bits for that dimension. Or striding with a step size of 2, that discards the less significant bit of that dimension. To get to more interesting things, let's look at large tensors. Tensors which do not fit into a single ciphertext. For those, we slightly generalize our layouts in that, in addition to our slot selecting bits, which is what we saw so far, we also have ciphertext selecting bits. These are bits that, for the given tensor element, tell us which ciphertext it maps to. And things get particularly interesting when we take a large tensor like this and we introduce gaps. Now, Felipe can represent this tensor with its layouts just fine. But the issue is, if we take this tensor in its current representation and then we try working with it on the subsequent operations, there will be overheads. We have data which would fit into one ciphertext, yet we're using 4. Fortunately, with Felipe, we can avoid this inefficiency. This is a procedure called compaction. Compaction lets us take any ciphertext selecting bit and move it into any gap bit. And we can do so very cheaply. We just have to rotate half of our ciphertexts and then add pairwise. And of course, we don't have to stop here. We have another ciphertext selecting bit, another gap bit. We can compact again. And voila. We have our tensor now represented using only one ciphertext that is fully packed. And it's worth emphasizing that Felipe's flexible layouts were crucial for enabling this. For example, here, the bits of the k dimension are now non-contiguous. But with Felipe, we get very cheap compaction, which is always possible provided we have sufficient data parallelism. Prior compilers didn't have flexible layouts, couldn't do compaction. As a result, they were forced to either remove gaps eagerly, which as we saw earlier in the talk is very expensive, or they would leave the gaps in, which then creates overheads down the road. Lastly, let's see how, given this layout representation, Felipe assigns layouts to tensors. We'll again be working through the same example, the sequence of matrix vector multiplies. Layout assignment proceeds in topological order. We first assign each input a row major layout. Whenever we have an expanding operation, we fill gaps eagerly. Binary operations require layouts to match. Here we get that automatically. And then whenever we have a contracting operation which introduces gaps, Felipe automatically inserts compaction eagerly to fill these gaps as much as possible. The only dose snag we get is when we have a binary operation with mismatched layouts. In that case, Felipe initiates backtracking to resolve this mismatch by changing one of the layouts. Here, this is fairly easy. One of the operands is an input, so we can just re-encode it under a different layout for free. Under more general settings, it might be necessary to perform a layout conversion. Once the mismatch is resolved, Felipe proceeds with layout assignment in topological order. This simple procedure is sufficient to achieve great results in our evaluation. We evaluate Felipe on a range of large FH applications, performing millions of operations each, yet representable succinctly in Felipe code. Further, Felipe compiles these large applications in mere seconds. As promised, Felipe generates programs which much outperform mildly tuned FH applications across a wide range of applications, and consistently outperforms prior work, sometimes quite drastically. Here, this is represented by an improved version of prior compiler chat. In summary, Felipe provides us with an easy-to-use tensor programming language for FHE, and by abstracting noise management and layouts, enables reuse and composition. And we get all these ease of use benefits without sacrificing performance. In fact, Philippe is the first FHE compiler to match the performance of manually optimized FHE applications. By eliminating the programmability challenges of FHE without sacrificing performance, Philippe eliminates the second obstacle to FHE adoption. Thank you so much for your attention, and I'm happy to take questions.
So we've got time for a few questions.
Hi, thanks for the talk. Could you comment on the memory requirements? I have two questions, and so this is the first.
The memory requirements of the compiler?
Yeah, in the evaluation, does it have an impact?
So this is evaluation of, so.
Does it increase the memory, or?
Let me just make sure I get your questions right. Does the compiler execute the memory required by execution, or does the memory?
No, I mean, instead of speed up, like, does it also?
Decrease memory?
Yeah.
So we haven't like precisely measured that. One of the things is generally the way we introduce speedup is by just performing few operations. In some ways, that's as you might notice, like our techniques we mentioned, they're not really specific to CPUs or accelerators. So the reason we can do that is because there's like lots of low-hanging fruit which we could get by just doing fewer operations in FHE. And as a result, by doing fewer operations, there's a smaller working set, which often also reduces the memory requirements.
Okay. The next question is, I know you mentioned to refer to the paper for noise management, but could you comment a little bit about like the point, I think in the first slide you mentioned, I think in the contributions, that it matches, the bootstrapping matches the manual?
Yep.
What does that mean?
So bootstraps are these very expensive operations which are set noise. You might even be at the case where like to first order the performance of your FHE application is determined by how many bootstraps you perform in total.
So you're comparing that with the standard, like the manual is like the standard one, and then you're comparing.
Manual is state-of-the-art manually optimized FHE applications where people have like looked very carefully where to place the bootstraps, so that you both don't perform it too frequently, but also you perform not narrow parts of the computation. So there isn't any good automatic algorithm, so we just compare with that, and we basically match the performance on the applications we study.
And is there any functional correctness argument in that? No.
In the sense of the bootstrapping placement?
Yeah.
So if you don't place bootstrapping, you're just, in some ways it's not a valid program. Yeah, it won't work correctly because you have noise issues. I can talk more about this offline because it requires some background, but essentially you need to perform bootstrapping every so often in order to not get incorrect results. And Philippe essentially places the minimum number of bootstraps it can under this constraint. So it always produces correct programs. Yeah.
I see. Okay. Thank you.
Thank you for your questions.
Hello. This was very cool. Thank you. I was wondering if you could comment on how likely would it be for somebody not you be able to add another backend? So how much of the, is it easy to add another accelerator specifically? Because I'm working on some, I can come and talk to you offline, but is that something that's kind of doable?
I think so. So I might misquote the number because it might be, don't have it in my slides, but I think our backend, which interfaces with like an FHE library, requires around like 400 lines of code, which is like 2% of our entire code base. So I think it's fairly manageable to add another one. Like there will be complexity which is related to your accelerator, which is not ready. But if you just want to translate our graph of FHE operations to your thing, it should be fairly simple.
Okay, cool. I'll come find you afterwards. Thank you.
Great.
Very cool talk. Thank you.
Oh.
My question is related to the backtracking. So is it, is it obvious, and if so, how do you know, maybe, that you'll always be able to find some sort of consistent assignment of layouts? Like, how do you know that you're never going to have to backtrack indefinitely and that there's like no way to kind of make sure that these operations match?
That's a good question, yeah. This is a moment which we didn't have much time to cover, but I'll try to explain in more detail here. So the way backtracking works is whenever we identify a mismatch, you have two chains of operations which lead to that. And we provisionally insert a conversion at either operand. This is kind of the middle part of the slide. Usually doing that conversion there is quite expensive, but if you move earlier in the computation, you can make it cheaper. So in this case, there are like two common cases for that, which are both illustrated here. In the top part of the slide, you see that we're converting right after a replicate. The tensor is bigger there, so there's more to convert. If you convert first and then replicate, some of the bits you get them in the right place in the layout for free during the replication. So that's cheaper. Or in the bottom slide, in the bottom case, you can just merge it with the input, which is also what we had in the in my example during the talk. So that's how you get it for free. But
I see. So worst case, you could just convert it every single step, and so you know that it's somehow possible. You just want to find a better way to do it.
And
okay.
And also,
that
like,
makes sense.
to make this efficient, we have like a more efficient algorithm for doing conversions, which is also described in our paper.
All right.
Thank you for the question.
Okay, so I think we need to move on to the server that next one. So let's thank the speaker again. And the next speaker will be Guillaume from Université Paris-Saclay.
Okay, so yes, as the chair said, I'm Guillaume. I'm a PhD student from the Université of Paris-Saclay, and I'm going to talk to you about quantitative robustness and what it is and how it's related to vulnerability assessment. So first off, nowadays we have a lot of really cool and really good bug finding techniques like fuzzing, for example. So we have projects like Google's OSS Fuzz that finds bugs in GitHub projects, and also things like Symbolic, which finds fuzzes the Linux kernel. But it's not just fuzzing. We also have other really successful techniques like symbolic execution and abstract interpretation. And so we're able to find a lot of bugs, but the thing is not all of these bugs have the same security impact, and we'd like to be able to tell the difference between them. One way to do that is to analyze their impact. So for example, does a bug cause an infinite loop or a memory corruption? But another very important factor is how reproducible those bugs are for an adversary. And what that means is effectively how much of a bug depends on uncontrolled inputs that come from the environment, like randomness, stack canaries, scheduling things, or undefined behaviors and initialized memories, things like that. One way to evaluate how this reproducibility is to use robust reachability. So what robust reachability is essentially it says that there is a controlled input that the attacker can choose that reaches the bug no matter what the uncontrolled inputs are. And in practice, we see that in some real-world bugs, we can actually show that we have some very strong robustness in this case. However, the natural question is, what about bugs that are mostly robust, so that happen very commonly, but not necessarily 100% of the time with the perfect controlled input? So, for example, here we have two bugs. One of them is triggered when the difference between an uncontrolled and a controlled input is equal to 1. The other one is triggered when the bitwise AND is equal to 1. So in the first case, the bug, if you assume that the uncontrolled input is uniformly distributed, it is quite unlikely to occur. However, in the second case, you can choose control equal 1, and then you have 50% chance of triggering the bug. So to sum up, both are reachable, but none are robustly reachable. So in this case, we'd like something that's a bit more nuanced. And what we want really is a quantitative measure of robustness. So something that can bridge the gap between plain reachability and robust reachability, which gives a really strong indication of robustness. So what we want to achieve, first off, is to give some formal definitions of that quantitative robustness, design some algorithms that can measure it, and implement them in a way that's automatic and scales pretty well. So the main issue with that is that in general, quantitative analysis tends to not scale very well. Things like model countings have some scalability issues. And also, we'd like to improve the performance over the robust symbolic execution that checks for robust reachability, because there are also some issues with that. Okay, so in general, our approach will be to take roughly the same approach as a robust symbolic execution, but essentially replace the robust reachability oracle with something along the lines of, do we have quantitative robustness above a given threshold? either on a path or on a collection of paths. And the interesting thing is that this problem, this quantitative robustness problem, is actually related to a problem called functional image set that comes from AI, but doesn't really have much applications in security as of now. So that's kind of interesting. And to sum up, our contributions are, first off, some definitions and theorems related to quantitative robustness. Quantitative robust symbolic execution, which is a quantitative version of robust symbolic execution. And also a reduction to functional image set for pathwise quantitative robustness, which is one of the first applications of functional image set in security, as well as our own approximated solver, and an implementation that we use to perform some experiments on real-world bugs. So first off, okay, how do we actually define quantitative robustness in details? So we reuse the threat model from robust reachability, which is that we have a program and a targeted location. It can be location in the program or within a bug oracle. And we split the inputs of the program between controlled inputs as the A set and uncontrolled inputs X. And so we define quantitative robustness as the maximum proportion of uncontrolled input X that reach the location for a fixed controlled input A. So in this case, it's a finite. It's a definition for finite input spaces, but we also give a definition with infinite countable input spaces in the paper. And as I said previously, we go from robust symbolic execution to a quantitative version by replacing the oracle with a quantitative robustness one. We have correctness with this algorithm, but also K completeness when we have path merging on top, which we call that algorithm QRC, quantitative robust symbolic execution plus. One point that I'd like to discuss is the importance of path merging with all of these algorithms. So first off, what is path merging? It's when you take multiple path constraints and you combine them in such a way that you get essentially a constraint for the union of those paths. So in this example, the merge path constraint for P1 and P2 would be essentially true. The issue with that is that it kind of adds complexity and it can cause some issues with solving for constraints afterwards. So if you consider symbolic execution, it doesn't really matter for reachability, because if you reach through a path, then it doesn't really matter if you combine them or not. However, for robust symbolic execution, it's very important, because if you don't have one path that's 100% robust, then you will say that no, there's no robust symbolic execution, even though sometimes you can have still robust reachability in the end. And the advantage of going for a quantitative analysis is that we can say, okay, maybe if we have 20% quantitative robustness, that's enough to say that's dangerous. And so in this case, we see that we have P1 with over 99% quantitative robustness. So in that case, we don't really care about path merging. That's not always the case, but it can be quite useful in practice. Also, we have some guarantees on lower bounds after some branches. You can ask about that afterwards if you want. So now let's talk about the reduction to functional image set. So first of all, context, we're doing binary analysis, so it's all bit-vector theories. So from now on, we're going to talk about finite input spaces. And so, okay, so is quantitative robustness model counting? Well, model counting counts reaching inputs, but in our case, control inputs aren't random. We choose them, so it doesn't really fit. So maybe it's projected model counting, but again, we have the issue that we're going to count the solutions for uncontrolled inputs, but for any controlled input. But we want the number of uncontrolled inputs reaching the location for the best controlled input. So in this case, it's still not projected model counting. And if we look at the definition of functional image set, I'm not going too much into the details of the definition, but essentially it's basically the same thing as what we said about quantitative robustness. And so there are some applications related to AI, a bunch of existing algorithms coming from AI conferences. However, the issue is that those algorithms aren't tested on quantitative robustness-like instances. And yeah, if that sounds like foreshadowing, then it is. So anyways, a basic approach to solve functional image set is to compile to a special form called decision DNNF with an additional constraint, which is called a layering. Essentially, you layer the uncontrolled variable. I'm not going to explain what it is, but Just remember that this idea of splitting and then layering one set of variables. And what this allows to do is to do model counting in linear time. However, the issue is that the hard part is compiling to the form, obviously. And the more layered variables you have, the more it's difficult. So one way to approximate the solution is to actually take some layered variables and just not layer them, and then apply the same algorithm. And that's what we call that relaxation. And what this gives us is an interval for the solution, for which we have some guarantees that depend on the size of the number of relaxed variables. Okay, so all of that is nice, but what does it give in practice? So with our experiment, we're interested in answering 3 questions. So first off, is quantitative robust symbolic execution actually more precise than robust symbolic execution? Can we avoid pass merging in some cases? And finally, what's the best functional image set solver for our use cases? So when it comes to precision, we took the benchmark from robust symbolic execution and we changed the ground truth for as is the robustness above 20%. In this case, we see that quantitative robust symbolic execution doesn't have a single false negative, while obviously robust symbolic execution says that in some cases you don't have robust reachability. But in those cases, you don't know if it's over 20% or not. So those are false negative in practice. And again, on the fault analysis benchmark, we're able to correctly classify attack traces based on their level of quantitative robustness. So we're able to distinguish nearly robust bugs from nearly unreproducible bugs, essentially. So then, can we avoid pass merging? So in this case, we did a case study on a stack buffer overflow from a CVE with and without a stack canary. So without a stack canary, we show that, okay, the bug is robustly reachable, as you'd expect. And we have one path with over 20% quantitative robustness. Okay, so now if we add a stack canary, we see that robust symbolic execution really doesn't like that, and it times out all the time. Same with quantitative robust symbolic execution when you have fast merging on top. However, we're able to show that there isn't a single path with over 20% robustness anymore. So that's already a pretty good hint of whether the bug is actually robust or not. And finally, so what about those functional image set solvers? So the first surprise is that almost all of the existing algorithms don't perform very well at all. You can see they're almost all bunched up on the left on the cactus plot. So that's not very good. However, there's one naive algorithm that performs really well. And our approximate relaxed algorithm performs also pretty well, even better, but it's approximate. So yeah, we actually have some algorithm that can be used to solve our instances. So to conclude, to sum up, bug replicability is very important. Quantitative robustness is a very precise indicator of the replicability of a bug. And we can measure it with quantitative robustness, reducing the pathwise quantitative robustness to functional image set. And the best solver for that are thus constraint and relax. And all of that is implemented in BinSec, version of BinSec that has quantitative robust symbolic execution that's available freely as an artifact. And just quickly, what can be improved? So improving the definition to widen it a little bit wouldn't be too difficult. I'll just say that the limiting factor is probably going to be related to algorithms. If you want, for example, to handle strings or linear arithmetic, you're going to have a hard time with symbolic execution could be possible, but actually solving functional image set on that, I mean, functional image set on that wouldn't necessarily make a lot of sense anyway, so that would be harder. But the definition could be adapted for that. So that's it. So if you have any questions, please go for them.
Thanks for a very nice talk, and we have time for some questions. So, if there are no questions yet, I have one. So, so one thing is, of course, that the attacker gets to pick the input, and then even if there's just one, they could just pick this one.
Yep. Yeah. I mean, that's the whole idea. So the attacker can, we assume that the attacker can choose the best control inputs, basically.
Right.
And we're trying to show that like how reliably the bug can be triggered with this input when there are a bunch of uncontrolled inputs.
I see. Any other questions? So I have another one. So of course you could also, like a different quantitative notion of security could be, for instance, like if you have a memory bug, how much can you, like which big of a memory region could you read, or how many other memory regions could you write to, or something like that?
Yes, so that's a very good question actually. So here we only considered the reachability of the bug itself, not really the how controllable the various parameters of the bugs are. That's a similar issue, but I'd say that it's complementary. Like it's adjacent. It would be nice to have both, but so in this case we tackled one half of the problem, and then there's still another half for people who are interested.
Do you think the same algorithm would work for that, or would you have to?
I think that in this case, taking into account actually trying to measure the robustness would be a bit much on top of trying to evaluate the values that are available for the different parameters of the vulnerability.
Okay. Any other questions? If not, then let's thank the speaker again. And next talk is by Jeremy Seek from Indiana University.
All right, testing. We good? All right. So today I'm going to be presenting the hard work of my graduate student, Tianyu Chen, who'll be finishing up here soon. He couldn't make it because of visa issues. He's here in spirit. Okay, so what we're talking about today is trying to do a gradual approach to information flow control. So we're wanting the programmer to be able to decide what parts of their program do they want runtime enforcement of the flow control, and what parts do they want static flow control. And there was some prior work that had a negative result that said you really can't do this. You can't have really gradual approach and IFC and like non-interference. Okay, so like if you want gradual languages, should satisfy something called the gradual guarantee. And of course, the IFC language should satisfy non-interference. And they showed a counterexample in their design that you couldn't have both. So what we're doing here is showing, yes, you can have both. You have to be, there's some sort of subtle little changes to the language design to get that. Okay, so I'm going to kind of do a quick reminder on how the dynamic and static enforcement works with IFC. So I'm sure for many of you this is easy stuff. So like in this example, we've got some private input coming in, and then we're trying to publish it publicly. Okay, so this is bad. And if you've got dynamic IFC enforcement, of course you'll get a runtime error on this program, right? And what's going to happen is, right, when you try to publish, it's going to look at the value that's coming through and look at a security label on that value and be like, okay, this thing is a high security value. We're not going to publish it. Okay, and so let's kind of just, this is going to become important later. And so like, where do these values get their labels from? Okay, there might be some primitive operations like this primitive input. You might have literals in your program that the programmer has annotated as being high or low security. And in some systems, dynamic information flow systems, you could get the security level from the execution context and use that for your value that you're creating. Okay. Okay, over on the static enforcement side, you can see now I've annotated the types with their security levels. And of course, when you try to call flip here, it's saying I want a low security Boolean, but we're giving it a high security Boolean, and you're going to get a type error at that point. Okay, so that's sort of, those are the obvious sort of explicit flow cases. Okay, then of course you've got your implicit flow, where maybe you've got some control flow that's impacting what's going on. So in this case, again, we've got a high security Boolean going into flip, and then we're using it in a conditional branch, right? And so the dynamic mechanisms of dynamic IFC are gonna, they're gonna know to sort of infect whichever result from this branch with like the high security tag, and then when you try to publish that, again, it's gonna fail, okay, thanks to these runtime mechanisms, okay? Over on the static side, you know, the type systems for static IFC are also smart about dealing with branching, and what's going to happen there is that the type system is going to see that, oh, we're branching on something that's a high security Boolean. Okay, so when I type check the branches, I'm going to know that those return values are high security, and you can't convert that to a low security. So again, so here we're going to have a nice type error to say you can't do that. Okay. Then to mix in a little bit more complexity, these counterexamples require sort of a combination of all these language features. We also have to worry about mutable pointers. So in this case, okay, now we're back to dynamic enforcement. We've got, we're creating a low security pointer, okay? And then we're branching on some high security value and then trying to write to the low security pointer, okay? So this could be bad. You could be leaking something here. But the dynamic enforcement mechanisms, there's this non-sensitive upgrade mechanism that when you try to do that right to the pointer, it's going to say, hey, wait a minute, we're in a high security context. You're trying to write to a low security pointer. We're not going to allow that to happen, okay? So this will, again, fail at runtime. And then on the static checking side, there's sort of a similar kind of static check that would happen that, okay, here, again, we're, you know, in the branch, we're trying to write to a low security pointer, but the static type system knows that we're in a high security branch and will disallow that also at compile time, okay? So that's sort of the standard static and dynamic IFC. Okay, now what if we go gradual? Okay, so what does that mean? So now we have this unknown security label, the star, okay? Kind of like a wild card. And so here, the Boolean to flip there, we're saying we're not committing to whether it's high or low security. And when that happens, it means we're not going to do static IFC, we're going to do dynamic IFC for that sort of four things related to that variable B, okay? And so for the branch here, we don't really know whether it's going to be a higher or low security branch. So we're going to use the runtime IFC mechanisms to deal with that. And so then what will happen is that at runtime, we'll know that it's high security. It's then going to be trying to cast a high security Boolean to bool of low, which is the return type. And at that point, that cast is going to trigger a runtime error, okay? So this will error at runtime, sort of at the moment where you're going from, you've got a value that doesn't match the type annotation that's expected. Okay, so that's sort of a little taste of gradual information flow control. So now let's get a little bit into these properties that you want to have. I think I'm going to skip over what non-interference means in this audience, but explain the gradual guarantee. So what the gradual guarantee says is, okay, let's say you've got different versions of the same program where we're just changing in, some of the security labels on our types. Like we might be replacing a high security with star or low security with star. So we're just adding and removing stars, okay? So we've got this lattice of like how precise are the security types, right? And so star is like the least precise, and then bool and high are incomparable, but they're maximally precise. Okay, so the gradual guarantee says that in the absence of errors, when you're adding and removing security annotations, that's not going to change the behavior of your program. Okay, you're going to get the same answer out. You're not going to change from like computing 42 to 24 or something. Okay, so no crazy changes of behavior. Now, if you start thinking about errors, if you're adding security annotations, it might be that you add the wrong annotation, and so that could trigger either a compile time error or a runtime error. Okay, so that can happen. If you're removing security annotations, going from like high to star or from low to star, that should not change the behavior at all. Okay, and so this is the gradual guarantee. We use it sort of as a litmus test for lots of different gradual languages out there. Okay, so this prior work that I mentioned before by Eric Tanter and Matthias Toro, they developed a language called GSLref. And so they came up with this counterexample where they had this program on the right that's more precise. That program runs just fine. Okay, there's sort of nothing wrong with that program. And then if you turn some of those high security labels into stars, the program on the left, it turns out, errors. Okay, and that violates the gradual guarantee. Okay, and the reason why it errors is that when you get to the assignment in the design of GSLref, what they're doing is they're like saying, okay, we're in a high security branch. But we don't know the security level of the pointer. And if it turned out to be low, we'd be in trouble, and we'd be breaking non-interference. So we better conservatively make sure, treat it as if it's low. Okay, so they error on the assignment, okay, at runtime. Okay, but this breaks the gradual guarantee. But wait, okay, let's look again at the dynamic, the sort of less precise program here. GSLref made the decision to allow the unknown security label as a label on values, which means that at runtime, you have values running around that have an unknown security label. This might seem sort of like a natural choice for a gradually typed language, but it turns out to actually be a slightly unusual choice, okay? So with gradual languages, you typically want to mimic sort of both a dynamic and a static version of the language and just kind of connect those. And so if you look at dynamic IFC languages, they don't have unknown as a runtime security label, okay? And then if you look at sort of just other gradually typed languages, not to do with IFC, we have unknown as a static entity, but we typically don't have unknown as a dynamic thing. Okay, usually you have all the information at runtime. Oh, this thing's an integer or this thing's a function. You're not unknown at runtime. Okay, so and then the other kind of weird aspect of allowing unknown on values is that the whole point of IFC is that your user is telling you oh, I've got some high security data, and that's an input to your system, and then your job is to protect that data, right? And so if they don't tell you what it is, what can you do about it, right? So it's a bit ill-posed. Okay, so that was GSLref. And so they were saying, okay, we've got this. We can't get the gradual guarantee. They got non-interference, but not the gradual guarantee. Then another paper came out about another system called GLIO. And what they did is they did two things. They changed two aspects of their language. They changed the way casts work so that, let's say you cast a low security value to high security. In GSLref, that would change the label on the value. But with GLIO, they said, no, if you don't change the label, you let it stay as a low on that value, then they made that change. Then you get the gradual guarantee. Though it's kind of interesting, they also made another change, which is they got rid of the star as a runtime security level. So they sort of made two changes to their language, and they claimed that the type-based reasoning one, the thing about cast, was what gave them the gradual guarantee. But when we saw that, we were like, when you change two things in an experiment, what about the other one? Okay. Then there was another paper, WildG, what they did is they said, okay, we're not going to do this non-sensitive upgrade checking on assignments. We're going to go with a more restrictive static analysis. And it turns out with that approach, you can also get the gradual guarantee. And so what we came along and said, well, hey, wait a minute. Let's focus on that last column. And if we were to just get rid of the unknown label as a runtime label, would that get us the gradual guarantee back? And then we could keep our, the casts working the way we want them to, allowing us to do type-based reasoning. And we can keep the NSU checking as usual. And so our short answer is, the too long didn't read, is yes. If you get rid of unknown as a runtime label, you can get back the gradual guarantee. Okay. So of course, we had to verify that that was the case. So we designed a calculus very close to the GSL ref calculus. It's got mutable references, first-class functions, and conditionals. The semantics is sort of how we normally do semantics for gradually typed languages, which is you do a compilation to a cast calculus that has explicit casts in it. And in an IFC language, you also have all kinds of stuff in your IR for the mechanisms of doing the dynamic checking for like implicit flow and things like that. And then the thing that's a little bit unusual or new for an IFC system is that we use a coercion calculus to it's this little combinator language for expressing how to cast from one type to another. And so, and part of that language is another set of sort of coercion calculus that just operates on security labels. Okay? And the reason why we're trying to go towards using coercions is that if you want space efficiency at runtime, then you need to be able, you kind of want to use coercions because they can be compressed. And so long sequences of them can always collapse down to just a few coercions. So this is sort of a stepping stone towards having an efficient implementation. So what do we prove? We prove the gradual guarantee. So that says if you have basically two versions of the same program, one is more precise than the other. If the more precise one runs to a value, then the less precise one should also run to a value. Okay, so it should behave the same. Okay, and then there's also the non-interference proof. Okay, which of course says that if you have some high security input, which we're just representing as a free variable here, and you've got maybe different values of high security inputs, your low security output shouldn't change, right? So no matter what, you're going to get the same public output. Okay, so we've proved that as well. Okay, so to sort of conclude, the non-interference property and the gradual guarantee property can coexist if we just make this subtle change of keeping those unknown labels out of the runtime security labels on values. Okay, we've done a AGDA mechanization of this calculus with a full proof of the gradual guarantee. We've got some but not all of the non-interference proof also mechanized. We do have a full non-interference proof for a slightly different language. Last year we had a different design that wasn't as good as this one, and but we had a full proof of that, and now we're still sort of updating that proof to match the new design. And then also, if you're interested in gradual typing and using coercions, then one nice thing about our development is that we show how do you do IFC using coercions. And with that, I will take questions.
Interesting talk. A very general question on this. So you usually have the problem that if you do not quantify information flow, you get a very high number of, let's say, technically correct but super uninteresting leaks. Like, is the password the one that I'm supposed to type in? Yes. Oh, that's a leak of my password. No, it's a normal login. So have you checked whether you can maybe quantify your approach so that you know how much is leaked? I mean, I can always check if the first character of my password is an A, then write something. If it is a B, write something. Then I leak the entire password, which is a completely different story.
So we have not looked at that at all. I think that's a great question. I guess maybe my question to the community is, so how much of this sort of gradual typing story is sort of orthogonal to other aspects of information flow, you know, and sometimes they might be very orthogonal, so it might be easy to add that kind of quantification, and then other times it, you know, you end up finding, you know, sort of conflicts like what we did here with the gradual guarantee. So
yeah, I was just asking that because we have looked into the into information flow as a generalized property of what you usually do as a data flow for like Android applications, Java applications. Then you just get tons of findings that are technically correct, but if you find that to developers, they'll just ask, what are you talking about?
Okay,
like,
so from a practical rollout standpoint, like you need to...
You're not leaking the password by telling you, hey, your login was correct. I mean, you have to show this somehow.
Right. Yeah.
Thank you.
Thank you for your talk. I was wondering, does your language support algebraic data types?
This calculus does not do algebraic data types. No.
Do you think it would be able, this approach would be able to support them?
I don't see why not. That seems like it would be a straightforward thing. I mean, usually like dealing with like mutable references is like the much more difficult.
Right. I was wondering because like the lib, let's say that you have like an unknown type and inside, and this is like an algebraic data type, and like the fields of this or the like elements inside these algebraic data types need a label in this type of fine-grained calculus. So that's why I was wondering.
Yeah, I mean, I guess like, are you thinking algebraic data type in a mutable setting or an immutable? So if it's mutable, then you're going to have all the same problems as mutable references. If it's immutable, I would think that there aren't really many issues.
So you should be able. Okay, cool.
Yeah.
Thank you.
Yeah.
Hey, so I actually don't have much background in this, but I had this question, like, does this like guard against side channel attacks? Like if there is, okay.
No.
And
at least I'm pretty sure no.
Okay. And the implementation of this is like, is it done in the compiler or it's something on like something like a pre-processing step before you compile some program?
You could do that. Well, there's going to be a runtime component of this, right? So, I mean, you could do a lot of stuff in the compiler, but then at some point you're going to be generating code that's going to also, you know, be doing runtime checking of things.
Okay.
And that you could have, your runtime could be in a library or, you know, you could be open coding it, and there's all the usual trade-offs, but.
Okay, so it's like some sort of like how smart pointers are there in C++. Like it tracks the ownership and deletes the ownership.
Yeah, yeah, I think
okay,
that's
thank
roughly,
you.
Yeah.
Thanks for a nice talk. So this might be
I liked your talk too earlier today.
Thanks. Yeah, perhaps my question might be also now to gradual security, but I'm curious about this approach could be scaled to the more complex control flows, like exception handling or first-class continuations, like call CC, effect handlers, and so on.
Whew. I don't know. I mean, I guess my question, I would immediately look to, you know, is there dynamic IFC systems out there so far that deal with those kinds of control flow issues?
Okay, so designing the dynamic control flow for such a more complex control flow would be the first starting point.
If there isn't already literature out there on that. I mean, usually when I'm sort of tackling gradual typing stuff, the hard stuff tends to be on the dynamic side, and then at the crossover points, and so yeah. But I think that's a very, very interesting question, though, how to deal with like continuations or delimited continuations.
Thanks.
Yeah.
Thanks for the great talk, and let's thank the speaker again. Right, and the last talk of the session will be given by Sam from MIT.
not hear. Aha, okay, perfect, perfect. Cool, so. Okay, so today I will tell you about our project on foundational integration verification of a cryptographic server. So using unit tests, one can find bugs within individual components of a system. However, that's not enough. One should also do integration tests in order to find bugs that sit at the boundaries between different components, which could be the result of different components making incompatible assumptions about each other's behavior. Now, in the world of software verification with proofs, many people do proofs about individual components. And unfortunately, in our opinion, what is done much less often is what we call integration verification. That is, put together proofs of several components to make sure that there are no bugs at the layer boundaries and component boundaries. If you do this kind of integration verification, something cool happens. Let's suppose that you have a proof about some cryptographic code generator that starts at a high-level elliptic curve math and compiles this down to C programs, and then assume that you have a proof that shows that the behavior according to this high-level math matches the behavior according to the C semantics. And then maybe you also have a proof of a compiler that shows that the behavior of the source program matches the behavior of the emitted RISC-V program. Then if these two semantics in the middle are actually the same, you can cancel them out and you can get a theorem that only mentions the top and the bottom specification. And then, if you play this game along a whole stack, of a whole system stack, you can get a combined end-to-end theorem that can serve as a concise description of the overall behavior of the system. And it only mentions the topmost and the bottommost semantics. So if you want to read code in order to understand what the system does, that is, if you want to audit the system, your auditing burden is much lower because you only need to read the topmost specification and the bottommost specification. And if we got some intermediate specification wrong, it doesn't matter because the upper and the lower layer relying on them are still compatible. We did a case study on this that we call the garage door opener. So it is a little cryptographic server, and you can send it packets to open the garage door and to close the garage door. And what we proved about it is that it only opens and closes the garage door in response to correctly authenticated commands. The stack includes 4 compilers and a diverse set of proof techniques that I will tour through later. At first, a few highlights about this project. So the proofs cover all the software that is running on our bare metal system. We have a Koch theorem that goes all the way from high-level math on elliptic curve crypto down all the way down to the binary representing the machine code. Our system includes input and output over the network and highly optimized cryptographic code. And most of the software is implemented in a high-level functional language, and yet the compiled code respects embedded systems conventions, and in particular, no garbage collector is needed. And we prove liveness and also that we don't run out of memory. And it is worth pointing out that this kind of fully end-to-end verification of all the code has only been carried out very rarely previously. Depending on how strictly you set the criteria, it has never been done, or maybe once, 2 or 3 times at most. So for the rest of the talk, I will first start with a little guiding principle, then show the description of our system, give an end-to-end theorem as the specification, and then do a tour through the diverse set of proof techniques that we're using. Let me start with our guiding principle. So as a PL researcher, you often encounter an opportunity to invent or use a nice framework. And this opportunity smiles at you, and of course you say, that's cool, let's do it. And then if you do this too much, you will end up with a bunch of very nice frameworks, nice specification styles, and nice concepts, but unfortunately they just don't fit together very well. And this actually happened to us, and so then you just give up, and there's no end-to-end theorem, and all the thing is lost. So we said, no, let's not do this. But in this project, we said KISS, which stands for Keep It Simple, Stupid. And by this, I mean that we chose a really simple specification, a really simple specification style. Namely, memory is represented as simply a finite map from words to bytes, a partial finite map. We use a very simple form of separation logic where clauses are represented, just have type mem arrow prop, and our specifications are either simple functional programs or they are predicates over I/O traces. We use weakest precondition signatures for all language semantics, and they happen to have the same signature as omni semantics, which appear also. We model network packets as lists of bytes, and we use concatenation of these lists of bytes. This simple specification style then allows us to unify a whole zoo of diverse proof techniques, which I will go through later. Now, a quick description of what our system does. So on the right, we have our little garage door server. On the left, we're using a laptop, but in a more realistic setup, this would be a little key fob. And in the more realistic setup, this would be wireless. In our case, we have an Ethernet cable between the laptop and the demo system. And the interaction is very simple. We send like a little packet that basically says, please send me a challenge. Then the server will send a challenge. And based on this challenge, we can send a open or close command. And if the cryptographic authentication is correct, the door will open or close. Now, let's see the end-to-end theorem that we proved. It says that for all RISC-V machines, if this RISC-V machine satisfies some initial conditions, and we run it according to RISC-V semantics, then some high-level property over the I/O trace will always eventually hold. So the reason this always eventually structure comes in is that we run one RISC-V instruction at a time, but the I/O spec specification only holds at the end of each high-level iteration, that is at the end of each iteration of the top-level event handler loop. So you might have to wait a little bit until you get to the end of this loop, but eventually you will get there. As expected, our top-level theorem only mentions the topmost and the bottommost semantics in our stack. And I will not say much more about RISC-V, but a little bit more about our top-level specification. It is a property over I/O traces, or also called event traces, and it says that a valid trace consists of a series of protocol steps, where each protocol step is one of the following. Either the network card was polled, but it timed out, or it returned no packet, or an invalid packet was received, or a packet was received that asked for a challenge, and a matching challenge reply was sent, or a correctly authenticated open closed door packet was received, and a corresponding memory mapped I/O request to the garage door was made, and then a new seed was derived from the current seed so that replay attacks are not possible. Now I'll do a tour through the different proof techniques that we used, And I will do so by showing you our system diagram. It's a little bit big. That's why I start by showing you the key for the diagram. And we have different kinds of arrows. We have previous work in this paper and different kinds of code. And the whole diagram looks like this. The point of this is not that you study each single box, but the thing I want to point out is that you can start at any box of this diagram, and then if you keep following the arrows, no matter where you go, you will always end up at the QED. So I will let you do this exercise a little bit. Pick any box, follow the arrows, and be pleased by how you will always end up at the QED. Okay, so now for a little tour through it. So we use from previous work, we used the Fiat Crypto framework to turn modular arithmetic expressed at a high level into fairly low level, pure administrative normal form code, basically 3-operand code. And the techniques involved there are partial evaluation and rewriting. Then we wrote a new compiler from the Fiat Crypto to Bedrock 2. Bedrock 2 is our subset of C that we support. And there we have a fast encoded input language. And the cool thing is that it also outputs separation logic specifications of the created functions with what we call read before write aliasing. So here's a little specification of a function that would transform a length 2 array. And the cool thing to point out here is that the caller of this function may choose if it wants to alias the input array and the output array. And so this is the input array, and here is the output array. And if it wants to alias them, the explicit frame R does not contain this input array, and the 3 yellow parts at the top in the pre and post conditions are all the same. On the other hand, if it wants to keep the input array and the output array separate, then the input array that you see in the first precondition goes into the frame in the second precondition and also in the post condition. Another technique that we use in the part for implementing modular inversion by using exponentiation by squaring is to simply use the partial evaluation techniques that we have available in the Cockproof Assistant, such as simple and unfold and CBN and those guys for these 2 steps that I marked here. And then we also have to implement multiplication of a scalar times an elliptic curve point. And there we have some part where the technique that we use is simply interactive proof of functional code in a proof assistant. And then once we arrive at what we call low-level Galena, which means functional code that is very close to imperative code but still functional, then we can use a tool called Rupicola, which allows us to derive imperative code from functional code. And it's a compiler implemented in the tactic language of Coq called Altac. And it can be configured by the user by adding custom compilation lemma to some hint databases. We also implemented a pseudo-random number generator using Rupicola. And then to implement the main garage door app, we used the Bedrock 2 program logic. It has pre and post conditions, and we incrementally prove the formulas that the weakest precondition generator of this program logic returns. And we reuse an existing IP checksum implementation, and we reuse the existing verified Bedrock 2 compiler to obtain RISC-V machine code. We reuse a lot of the network of previous networking code, but we had to implement new code for transmit functionality. And there we again used the Bedrock 2 program logic, and our specifications combine separation logic and propositions over the I/O traces. And finally, there are 2 functionalities that are not expressible in our Bedrock 2 subset of C, namely memory mapped I/O and the infinite event handling loop at the top level. And for these, we use something we call like mini compilers. They're really, really simple pieces of code that emit a few assembly snippets. So with AMAM.io, we use external calls to represent them in Bedrock 2. And then this mini compiler simply replaces the external call by stores and loads in RISC-V. And for the top-level infinite event handling loop, the problem in Bedrock 2 is that Bedrock 2 semantics require proving termination for all programs, but there the point of this whole loop is that it does never terminate. So we use this little mini compiler that simply calls a designated init function once and then repeatedly calls the loop body function. And then with all that, we can put everything together into this one QED that spans the whole system. We did some performance measurement as seen from the client that opens and closes the garage door. So if we use our implementation and compile it with the verified Bedrock 2 compiler, one interaction takes about 0.47 seconds. If we replace the verified Bedrock 2 compiler by GCC, it only takes 0.12 seconds. But the interesting part is that if we substitute all the crypto part by the state-of-the-art boring SSL crypto code that runs in Chrome, the performance doesn't really change. So from this, we can conclude that the only remaining performance bottleneck in the whole thing is the Bedrock 2 compiler, which is not surprising because we put basically no effort at all into optimizing this compiler. And then the other part is also that the optimizations that we did above the Bedrock 2 compiler actually paid off in the sense of it is as good as boring SSL if we use GCC. So to conclude, using this simple specification style allows us to combine a diverse set of proof techniques. We use a high-level functional language for many parts, but still we can run on an embedded system without garbage collection. We provably won't run out of memory. We combined 4 compilers as well as a handwritten code, and we proved everything from high-level elliptic curve math down to RISC-V machine code, and as expected, all the intermediate specifications cancel out in our final theorem. So with that, I'm done, and I'm happy to take questions.
Great, we have time for 1 or 2 questions.
Yeah, so thank you for your great talk. I was wondering, have you considered going lower, say not to RISC-V, but to some abstract specification of PMOS and NMOS transistors?
Not quite that far, but in a previous paper, we combined the software proof with a hardware correctness proof, and there we had a little pipeline processor and went all the way down to a hardware description language called BlueSpec, which is still not quite as low as you want. My advisor, I think, did try to hire people who want to go lower, and he sits right in front of you, so people, I think this is still a thing, and we want to, I would say.
Thank you.
Very cool, of course. Since you're able to use a lot of existing systems, compilers, I was wondering if you had any particular lessons learned or challenges about how they all fit together, or maybe if just one thing had been different, they would have fit together much better.
Well, okay, one, I mean, I want to show you this one. I think this one matters. Yeah, this one matters. Then what would we want to do? You ask about the thing that worked a bit less well, I think, right? And or the things we learned, and yeah, I think I think at reusing Rupicola, that's not the part that I did, but there I think that worked well for the domain in which it was designed. But then for the part in adding the pseudo-random number generator, the Cha-Cha 20 thing, we extended it with something to use local variables as to instead of memory, and it was cool that it worked, but my colleague reports that it was hard. So, I mean, yeah, the question is, trade-offs of, what tool do you want to use? How far can you push each tool to its boundaries? And Also, the expert on Rupicola is Glemma, sitting right here. I think he didn't, but he's not the one who found it hard to use because he's the one who wrote it. But you can,
Great, thanks. So if there are no more questions, let's thank the speaker again. And this was the last half of the session.